Hello, and welcome to the sleepy universe. Let the room around you slow down for a little while. Perhaps the lights have grown softer. The sounds in the distance are no longer as clear as they were during the day, and within that quiet, we can step away from everything still unfinished and turn toward a question that is distant, dark, and strangely peaceful. If a black hole is a place where everything goes in and never returns, could it ever become its complete opposite, a white hole, where light and matter can only come out? In the familiar imagination, a black hole often appears as an enormous abyss in space, silently drawing everything into darkness. But in science, a black hole is not simply a hole, nor is it an empty space carved out of the universe. It is a region of spacetime curved so intensely by gravity that every possible path within it leads farther inward. Even light, the fastest thing we know, has no route back to the outside universe once it crosses that boundary. This boundary is called the event horizon, a beautiful name because it resembles the horizon at sea. We can look toward it and imagine what lies beyond, but we cannot directly see what is happening on the other side. What makes a black hole remarkable is not only its darkness. Something deeper lies in the way it forces us to rethink time, matter, and the meaning of an ending. When a massive star reaches the end of its life and its core collapses beneath its own weight, matter is compressed into such a small region that familiar ideas begin to lose their footing. Space is no longer a stable stage on which events unfold. Time is no longer a steady current measured by the clock on the wall. Near a black hole, time can pass more slowly, light can be stretched out, and what feels like a brief moment to a falling object may appear to a distant observer as a scene lasting almost forever. For a long time, we have been accustomed to thinking of black holes as full stops. A star goes dark, its core collapses, matter disappears from view, and beyond the event horizon lies a silent realm from which no signal can return. But modern physics rarely allows a story to end so easily. The deeper scientists look into black holes, the more difficult the questions become. Does matter that falls inside truly disappear? Is the information about everything that entered erased from the universe? And if the equations of general relativity allow a black hole to exist, could reversing time within the mathematics reveal another strange possibility? A white hole? A white hole, if such a thing exists, would resemble the reverse image of a black hole. Nothing from the outside could enter it, while light and matter could emerge. If a black hole is a doorway that opens only inward, a white hole is a doorway that opens only outward. The idea may sound like something born from imagination, but it did not begin in science fiction. It arose from serious attempts to understand the geometry of spacetime, where the equations sometimes permit solutions that are more elegant, more unusual, and more difficult to test than anything a telescope can immediately reveal. Still, on this journey, we will not rush to treat white holes as something already discovered. So far, science has no conclusive evidence that they exist in the real universe. They remain a theoretical possibility, an idea resting at the boundary between what is known and what cannot yet be tested. But it is often at that boundary that physics becomes most fascinating. A white hole does not merely raise questions about an unusual kind of cosmic object. It touches something deeper. Is the interior of a black hole truly the final destination, or is it simply a place where our present theories are not yet powerful enough to see any farther? There is a gentler way to imagine this. Think of a ball being pushed deep beneath the surface of the water. The farther down it goes, the greater the pressure becomes, the darker the water grows, and from above, the ball may seem to have vanished. But if some limit prevents it from being pushed any deeper, it may eventually rebound and rise again. Some models of quantum gravity have explored a similar image for black holes. Instead of matter collapsing forever toward an infinitely dense singularity, perhaps at an extremely small scale, where quantum mechanics becomes important, the collapse comes to a halt, reverses direction, and then, in the very distant future, emerges into the outside universe as a white hole. This is not science's final answer. It is a possibility still being studied, One way of thinking about the places where general relativity and quantum mechanics have not yet fully come together. But the possibility is beautiful enough for us to move slowly through it. Because if a black hole could become a white hole, then perhaps the universe does not operate through endings as simple as we once imagined. An ending may only be an immensely long state of waiting. A dark region may not be a place where everything is erased, but one where physics is hiding a deeper chapter of time. Perhaps the most comfortable way to approach this story is to begin with what science understands fairly well: what a black hole is, why light cannot escape, how time changes near the event horizon, and why the idea of a singularity is still regarded as a sign that our current picture is missing important pieces. From those foundations, the story naturally leads to the information paradox, one of the most debated problems in modern physics, and then gradually opens into bolder ideas about white holes, quantum bounces, and the possibility that time may be experienced very differently in the most extreme regions of the universe. And perhaps, whether these ideas ultimately prove right or wrong, their value does not lie only in the answer. Sometimes, what is more compelling is the reason scientists continue asking the question. Black holes have long been places where the limits of our understanding become especially clear. They remind us that the universe is not made only of familiar things, such as stars, planets, and galaxies, but also of regions where ideas that seem certain space and time themselves begin to behave in unfamiliar ways. And within those dark regions, science continues to search patiently for the smallest clues, hoping to understand a little more about what may be happening beyond horizons that light can never cross. When we hear the words black hole, it is easy to imagine a completely dark emptiness in the middle of the universe, like a hole torn into the fabric of space, where everything falls in and disappears. The image is deeply compelling because it is simple, easy to picture, and mysterious enough to have made the black hole one of the most recognizable symbols of modern astronomy. But if we slow down for a moment, we begin to see that the name black hole is both accurate and misleading. It is accurate because, from far away, a black hole truly does appear as a dark region, a place that produces no light of its own and allows no light to escape once it has gone too far. But the name can also be misleading, because a black hole is not a hole in the ordinary sense. It is not an empty space, a tunnel, or an open mouth waiting between the stars. It is a region of spacetime where gravity has become so intense that every possible path bends inward. To get a sense of this, we can begin with something very familiar: the gravity beneath our feet. At this very moment, whether you are lying in bed or sitting quietly in your room, Earth is still pulling you downward with a gentle, steady force. We are so accustomed to it that we barely think about it. It holds the atmosphere around the planet, draws rain toward the ground, keeps a cup from floating off the table, and gives our bodies the feeling of belonging to a surface. Earth's gravity is strong enough to hold us here, but not strong enough to prevent light from escaping. Light from the lamp in your room can still reach your eyes. Sunlight can still leave the surface of the sun, cross space, and arrive at Earth several minutes later. In these familiar places, space and time still behave in ways that everyday life can comfortably endure. A black hole becomes something different when matter is compressed into such a small region that gravity is no longer merely an ordinary pulling force. It becomes a profound distortion of space-time itself. Einstein's general theory of relativity does not describe gravity as an invisible cord pulling one object toward another. Instead, it describes gravity as the way mass and energy curve the structure of space and time. A planet bends space-time around it slightly. A star bends it more strongly. A black hole is a case where that curvature becomes extreme. If we imagine space-time as a soft surface, Earth would create only a shallow depression, the sun would form a deeper valley, and a black hole would resemble a slope so steep that every nearby path tilts toward one irresistible direction. Still, the image of a sagging fabric is only an analogy. It helps us picture the idea, but it should not be taken too literally. A black hole does not sit below the universe like a well, because real space has no single downward direction shared by everything. What happens is far more subtle. The paths through spacetime itself have changed. An object near a black hole is not pulled inward because some mouth is sucking it in like a vacuum cleaner. It simply follows the most natural path spacetime allows, much like a marble rolling along the slope of the ground. The closer it comes to the black hole, the more sharply those paths lean inward, until a very special boundary appears. That boundary is called the event horizon. It is one of the most important ideas in the physics of black holes, and also the source of many misunderstandings. The event horizon is not a solid shell. If an imaginary spacecraft crossed it, the people inside would not strike a wall, hear a crack, or see a glossy black surface closing behind them. According to general relativity, when crossing the event horizon of a sufficiently large black hole, a falling observer might not notice anything unusual at that exact moment. The difference lies in the future of every path ahead. From inside the event horizon, even if light tries to travel outward, every path available to it still leads deeper toward the center. This is not because the light has grown weaker, but because space-time has curved so severely that going outward is no longer a possible direction into the future. A more familiar image is a river flowing toward a waterfall. Far from the falls, a boat with strong enough oars can turn around and move upstream. A little closer, the current becomes stronger, and returning is more difficult, though still possible to imagine. But eventually, there comes a point where the water flows faster than any boat could ever row against it. The boat may still be intact, and the people aboard may still feel themselves floating normally on the water, but from that moment on, every realistic path leads toward the edge. The event horizon of a black hole can be understood in much the same way. It is not an object. It is the boundary beyond which returning is no longer possible. For this reason, a black hole does not need to suck in everything in the universe to be extraordinary. One common misunderstanding is that if the sun suddenly became a black hole with the same mass, Earth would immediately be swallowed. But if the mass remained unchanged and Earth began in the same orbit, the gravitational pull at Earth's distance would remain essentially the same. Our planet would continue orbiting that mass, except there would no longer be sunlight or warmth to sustain life as we know it. A black hole is not a cosmic vacuum cleaner sweeping up everything from far away. It becomes most dangerous and strange close to the event horizon, where the distance is small enough for the curvature of space-time to become impossible to ignore. A black hole is dark, not because it is made from some kind of black material. It is dark because light cannot escape from inside the event horizon and reach our eyes, our telescopes, or any detector outside. Yet the universe around a black hole can be extremely bright. Gas and dust falling toward it may become intensely heated as they spiral through an accretion disk. Matter collides, rubs together, accelerates, and releases X-rays and other powerful forms of radiation before some of it crosses the final boundary. This creates a quiet paradox. The black hole itself does not shine in the ordinary way, but the region surrounding it can be among the brightest and most energetic places in the universe. When astronomers say they have seen a black hole, they usually do not mean that they have directly observed its dark interior. They observe its effects. They see stars racing around an invisible object at extraordinary speeds. They see hot gas glowing as it falls into a region of extreme gravity. They detect gravitational waves from black holes merging together, tiny ripples spreading through space-time itself after a violent event far away. And in recent years, humanity has even created images of the shadowy regions around supermassive black holes, not with a single telescope, but by combining radio telescopes across the Earth to form an observing eye, nearly the size of the planet. Even those famous images must be understood carefully. The dark region in the center is not a direct photograph of a black hole's surface. It is the black hole's shadow against the hot light around it, distorted by immensely powerful gravity. Light nearby does not travel in the simple straight lines we are familiar with inside a room. It bends and curves, wrapping around the black hole and forming an uneven ring of light, whose brighter side is often connected to matter moving toward the observer. The image does not make the black hole any less mysterious. Instead, it shows that even darkness can be recognized by science through the things that happen around it. Here, we can slow the pace a little. There is no need to imagine a black hole as a loud or violent spectacle. From a great distance, it may remain as quiet as a dark point in a sea of stars. It calls to no one, does not chase distant planets, and does not disturb the order of the cosmos with some endless hunger. It simply exists as a natural consequence of gravity, when matter is compressed to an extreme limit. Yet that consequence carries us into a realm where everyday intuition is no longer enough. We are accustomed to thinking that if there is a way in, there must also be a way out. We assume that if time passes one way here, it must pass in the same way somewhere else. A black hole gently overturns those assumptions, not through words, but through the very shape of spacetime around it. This is essential to the larger question at the heart of our journey. Before asking whether a black hole could become a white hole, we first need to understand that a black hole is not an ordinary object that can simply be turned inside out like a piece of clothing. Nor is it a cave with an entrance and an exit. It is a structure within space-time, a region where the meanings of outward and moving forward are no longer the same as they are in everyday life. If a white hole is the reverse image of a black hole, that reversal would involve far more than changing from black to white. It would be a much deeper reversal, the reversal of what may enter and what may leave, and of the direction in which all possible paths into the future are allowed to unfold. What matters most, then, is not the image of a frightening dark region, but the way a black hole forces us to reconsider space and motion themselves. Outside it, objects may still orbit, light may still pass by if it does not come too close, and the universe continues to move with its vast and quiet order. But at the event horizon, familiar intuition begins to fail. No wall appears, and no signal announces that a boundary has just been crossed. Yet every possible path from within leads in the same direction. And when the structure of space-time can change so profoundly, another consequence becomes difficult to avoid. Does time near a black hole still pass in the same way it does in the more familiar regions of the universe? If a black hole only changed the paths of matter and light, it would already be strange enough. But what makes a black hole one of the deepest places in physics extends beyond space. It also touches time, something we experience in everyday life as a steady current, quietly passing through every room, every street, every morning, and every nightfall. On Earth, 1 second on the clock hanging on the wall seems to be the same as 1 second on a phone, at a train station, in a hospital, in a garden, or in the quiet room where you are listening now. We may be late or feel that a day has passed very quickly or very slowly, but those are experiences within the mind. In ordinary physical terms, we are accustomed to believing that time is a shared background, a single steady rhythm for the entire world. Relativity changed that belief in a way that was subtle, yet profound. Time is not an enormous clock hanging outside the universe, forcing everything to move at the same pace. Time is connected to space, motion, gravity, and the position of the observer. Where gravity is stronger, time can pass more slowly than it does where gravity is weaker. In everyday life, this difference is extremely small, far too small for the body to notice. But it is real, it can be measured, and even satellite navigation systems must account for it in order to work accurately. The universe does not use a single clock. It uses many clocks, and each one carries with it the particular conditions of its place in space-time. Near a black hole, that difference is no longer a minor adjustment. Gravity becomes so intense that, from the perspective of a distant observer, time appears to slow dramatically. Imagine a glowing clock being lowered gradually toward the event horizon. From a safe distance, an observer would see the light from the clock grow redder and fainter, while each tick seemed to stretch longer than the one before. The clock has not broken in the ordinary sense, nor has it somehow decided to run more slowly. What happens is that light, leaving a region of intense gravity, must climb out of an immense depth in spacetime before it can reach somewhere farther away. In the process, the light loses energy, its wavelength grows longer, and the signals carrying the clock's rhythm arrive more and more slowly to the person watching from outside. This image can make it seem as though an object falling into a black hole must remain frozen forever at the event horizon. But that is only half the story, and it is the half seen from the outside. For the falling object itself, if the black hole is large enough that tidal forces do not tear it apart near the boundary, time continues to pass normally within its own frame of reference. A falling observer would not see the watch on their wrist suddenly stop. Their heart would keep beating, their thoughts would continue, and the small lights inside an imagined spacecraft would still travel from one place to another. In that local experience, crossing the event horizon might not be marked by any clear or dramatic moment. The difference lies in what the observer can no longer do: send a signal back to someone outside after passing the boundary of no return. It is this difference between the two perspectives that makes a black hole so unusual. From far away, we may see a falling object appear to slow down, grow redder, become dimmer, and finally disappear from view. From the perspective of the falling object, the journey continues without stretching endlessly in its own experience. These two descriptions do not necessarily contradict one another. They belong to different observers under different conditions in spacetime. This is one of the central lessons of relativity. The universe does not always give us a single, simple story that looks the same from every location. There are events whose appearance depends on the observer's position, motion, and depth within a gravitational field. To feel this through a gentler image, imagine two rooms separated by an enormous distance. In the first room, far from the black hole, a clock hangs on the wall, its hands moving with a soft and steady rhythm. In the second room, near the edge of a black hole, there is an identical clock. If each person looks only at the clock in their own room, both will feel that time is passing normally. But if the distant observer could watch the light signals sent from the clock near the black hole, they would see the rhythm from the second room stretched out. Each second near the black hole, when viewed from far away, would no longer resemble an ordinary second. It would seem to be spread thin across the curvature of space-time, quietly lengthening in the darkness. This is not merely a minor detail in the physics of black holes. It is an important part of the question of white holes. Many speculative models in which a black hole might transform into a white hole depend on the enormous difference between time inside and time outside. Some process deep within the black hole might, from its own perspective, unfold over a very short interval. Yet for the outside universe, because of the stretching of time near the event horizon and within an extreme gravitational field, that same process could correspond to an immense span of time. In other words, if some transformation occurs within the core of a black hole, it may not appear to us immediately. It may be delayed until a future so distant that it lies far beyond ordinary intuition. We might picture a grain of dust falling into the darkness. For the grain itself, the downward journey may be brief. But to someone standing very far away, the final light from that grain is stretched, weakened, and slowly lost, like the sound of a small bell traveling down a hallway that seems to grow longer and longer. The closer it comes to the event horizon, the more difficult it becomes for any signal to return. Space does not merely hold matter inside, it also slows the way the last traces of information are carried outward. To the distant observer, the black hole seems to turn every fall into a scene that slows without end, not because the universe has stopped, but because light is struggling to escape from a place where the future itself has tilted inward. There is one point here that must be stated carefully. When we say that time near a black hole passes more slowly, it does not mean that someone there would feel trapped inside a slow-motion film. Each person always lives within their own time. If you were near an object with powerful gravity, your heart would still beat according to the rhythm of your body, your breathing would still feel familiar, and the clock you carried would continue ticking normally for you. The slowing becomes apparent only when your time is compared with that of someone in a weaker gravitational field. It remains a physical quantity that can be measured by clocks, but clocks in different places do not necessarily agree with one another completely. There is something beautiful in this truth, because it brings an idea that seems so distant closer to everyday life. Even on Earth, time at sea level and time at the top of a mountain are not perfectly identical, though the difference is extraordinarily small. An atomic clock placed slightly higher in Earth's gravitational field will run slightly faster than one placed lower down. Over a human lifetime, that difference is almost impossible to feel, but in precise physics, it exists. And when the same principle is carried near a black hole, where gravity is no longer as gentle as it is on our planet, that tiny difference becomes a vast abyss of time. Perhaps this is why black holes have always carried a sense of strangeness that goes beyond darkness itself. Darkness merely prevents the eyes from seeing. A black hole, however, makes the very way we measure time depend on where we are in the universe. It unsettles one of the deepest human assumptions, the belief that everything is moving through the same shared present. When a distant star shines, its light takes time to reach us. When a planet circles its star, we see it as it existed at some moment in the past. The universe is already a tapestry woven from many different moments in time. A black hole simply carries that truth to its most extreme form, where the difference between here and there is not only a matter of distance, but also of the rate at which time passes. In the quiet of this moment, there is no need to hurry into the equations. We only need to hold on to the image of two clocks. One is far away, where space-time is relatively flat, and light can travel freely. The other is near the event horizon, where its signal must climb out of such a deep curvature that every pulse returning to the outside is stretched longer than the one before. The two clocks are not disagreeing, they are simply telling two different parts of the same universe. And through its gravity, the black hole makes the distance between those two stories so great that we are forced to reconsider what right now truly means. When we think about the possibility of a black hole becoming a white hole, this slowing of time becomes an important key. If matter falling into a black hole does not simply disappear, and if some quantum mechanism deep within prevents the collapse from continuing forever, then that event might occur within a finite amount of time from the perspective of the interior. But for those of us outside, it could be stretched across a span longer than the current age of the universe. A single blink in that deepest region might correspond to billions of years passing in the space beyond, or perhaps to timescales far greater still. This makes the question of white holes feel less like a sudden miracle, and more like a physical possibility that must be considered carefully. If a black hole can undergo a transition, it does not need to do so according to the familiar rhythm of our own time. It could remain silent through nearly the entire history of the universe as we know it, while within, a deeper process may have already finished long ago according to its own clock. From the outside, we would see only a dark region continuing to endure. From another perspective, the story might have advanced much farther. This has not been proven, but it is one reason time cannot be ignored in any serious discussion of black holes and white holes. And once we begin to notice time, a black hole is no longer merely a place from which light cannot escape. It becomes a region where the layers of present, past, and future are placed under the pressure of gravity. It reminds us that the universe is not a simple stage where every event unfolds beneath the same light and to the rhythm of the same clock. In extreme regions, the stage itself can tilt, contract, stretch, and force time to follow unfamiliar paths. From there, the next question begins to emerge more naturally. If both space and time are pushed to their limits near a black hole, is its deepest interior truly an infinite endpoint? Or is it simply the place where our current theories are no longer sufficient to describe what happens next? Beyond the event horizon, a black hole is no longer an object that can be seen through light, nor is it a place from which ordinary signals can return. From the outside, everything that falls in gradually grows dimmer, shifts toward red, and then disappears from view. But in the picture described by general relativity, the journey does not end at the boundary. Once matter has crossed the event horizon, it continues deeper into a region of intensely curved spacetime, where every possible path into the future leans toward the center. At that center, the classical model leads to a very unusual concept, the singularity. It is a place where the equations suggest that the density of matter and the curvature of spacetime may become infinite. A star that was once immense, shining for millions or billions of years, may leave behind, after its collapse, a region where all its remaining mass is compressed beyond the limits of ordinary intuition. There is no longer a stellar surface, no glowing outer layer, and none of the familiar structure of matter found in ordinary planets or stars. What remains is an extreme mathematical result, where general relativity seems to carry everything toward one deepest point. The word infinite must always be approached very carefully in physics. It is not simply an enormous number that we can imagine and then continue adding to. It is more like a sign that the language we are using has begun to lose its ability to describe what is happening. When a quantity in an equation becomes infinite, nature is not necessarily telling us that some real object out there truly possesses an infinite value. Many times in the history of science, an infinity has appeared where a theory was pushed beyond the region in which it worked best. It is like a map that is highly accurate along familiar roads, but as it reaches an unexplored mountain range, the lines begin to overlap and eventually give way to a blank space. General relativity is such a map, though it is one of the greatest maps humanity has ever created. It describes gravity not as a simple, invisible force, but as the curvature of space and time. It explains why light bends as it passes near a massive object, why clocks run differently in different gravitational fields, and why two merging black holes can make spacetime itself ripple in the form of gravitational waves. From planetary orbits to distant galaxies, general relativity has repeatedly held firm against observation. But as we move closer to the center of a black hole, where matter is compressed to an extremely small scale and gravity becomes extraordinarily strong, the map begins to reach the edge of its own territory. At such tiny scales, quantum mechanics can no longer be ignored. The world of atoms, electrons, photons, and quantum fields does not behave like the world of balls, planets, or stars. Matter can no longer be pictured only as tiny particles resting in perfectly definite locations. Energy, probability, quantum fluctuations, and the deepest limits of measurement begin to enter the picture. In everyday life, these effects are usually hidden by the large scale and stability of the world around us. A table still appears to be a table. A stone remains still on the ground. A room keeps its clear and familiar shape. But deep inside a black hole, where an enormous amount of mass is forced into an extreme region, those microscopic rules may become impossible to avoid. The difficulty is that general relativity and quantum mechanics have not yet been brought together into one complete framework. One describes spacetime as a smooth, continuous structure that curves in response to mass and energy. The other describes the microscopic world through probability, quantization, and limits that classical intuition struggles to accept. Under most conditions, these two languages can be used separately. For the orbit of a planet, general relativity or classical mechanics is usually enough. For the structure of an atom, quantum mechanics is the appropriate language. But at the center of a black hole, both extremely strong gravity and extremely small scales appear at the same time. Neither theory can quietly remain outside the picture. This is why the singularity is more than a strange result in an equation. It is the place where the two great foundations of 20th century physics meet in a region for which humanity still has no complete answer. If we use general relativity alone, the collapse appears to continue toward infinity. But quantum mechanics often prevents extremely compressed states from behaving in such a simple way. At a very small scale, effects may appear that the classical model cannot see. They could change the final outcome of the collapse, or at least make the picture of an absolute infinite point far less certain. A gentler way to imagine this is to think of a calm surface of water seen from far away. At a distance, the lake appears smooth, continuous, and unbroken. A boat drifting across it leaves soft ripples behind. But at an extremely small scale, the water is no longer a perfectly smooth surface. It is made of countless molecules, constantly vibrating, colliding, and moving. The smoothness is an accurate picture on a large scale, but it is not the final description at every level. Spacetime may be similar in some areas of research. It appears smooth and continuous across astronomical distances, but when pushed to the smallest possible scales, a deeper structure may begin to reveal itself. If spacetime truly has a quantum structure at its deepest level, then the collapse inside a black hole may not continue forever toward an infinite point. There may be a limit beyond which matter cannot be compressed in the classical way. The curvature of spacetime, instead of increasing without end, may reach a region where quantum effects alter the evolution of the system. The words may and might are important here. These are not conclusions. They are theoretical doors opened by the question that the singularity places before modern physics. From the outside, no one can observe this region directly. The event horizon prevents ordinary signals from returning. Telescopes can observe light from the accretion disk, measure the motion of nearby stars, and detect gravitational waves from mergers, but they cannot look directly into the deepest interior. Whatever lies beyond that boundary must be inferred through theory, mathematics, indirect evidence, and consistency among different branches of physics. This makes a black hole unlike a planet, a star, or a cloud of gas. From those objects, light can still carry information outward. With a black hole, the most important region lies within a realm that sends no messages back. That silence does not make the question disappear. On the contrary, it makes the question even deeper. If matter falls into a black hole and continues toward the singularity in the classical model, is the information carried by that matter still preserved somewhere? If quantum mechanics is correct in saying that information cannot simply be destroyed, then an infinite endpoint at the center of a black hole becomes difficult to reconcile with the rest of physics. And if the singularity is not the true ending, then behind the veil of the event horizon, a process may be unfolding that our current theories have only begun to touch at the edges. There is no need to turn this into an overly violent image. It may be enough to imagine a distant region of darkness where a star has left its entire weight behind in a structure smaller than anything ordinary experience can picture. The familiar layers of matter are gone. Light has no path back out. Time inside and outside can no longer be compared easily. At the deepest point, the classical equations lead to an extreme limit, as though the road on a map had ended at the edge of a region not yet drawn. No explosion needs to echo through the imagination. No image needs to be blindingly bright. There is only a question resting quietly in the darkness. Does nature truly allow everything to reach infinity? That question leads directly into the search for a theory of quantum gravity. Some models suggest that the interior of a black hole may contain a state of extreme compression that is not infinite. Different theories and mathematical approaches give this state different names. In some ideas, collapse may be replaced by a transitional phase, where matter reaches an enormous density but no longer continues downward in the classical sense. From this perspective, a black hole is no longer merely a silent endpoint of spacetime. It may instead be an intermediate state immensely long, profoundly deep, and extraordinarily difficult to observe from the outside. Models like these are still far from being supported by conclusive evidence. They do not allow us to say that every black hole will become a white hole. They reveal only a possible direction of thought. If the singularity is a sign that the theory is incomplete, then a deeper theory may change our picture of the black hole's interior. In a new framework that includes the quantum effects of gravity, matter may not be compressed to infinity. Time inside may not end in a simple way, and what was once called the center of the black hole may become a transitional region that remains invisible from the outside. From a great distance, a black hole may still rest quietly among the stars as a peaceful region of darkness. Nearby, celestial bodies continue in their orbits, hot gas continues to glow, and faint signals still reach telescopes after long journeys through space. Yet within the equations that attempt to describe its deepest interior, a quiet tension remains. General relativity carries the story toward a singularity. Quantum mechanics leads physicists to suspect that this infinity cannot be the final answer. Between them lies the space where ideas about quantum gravity, a possible rebound, and eventually white holes begin to emerge. Matter falling into a black hole cannot send a message back. Light cannot escape from within the event horizon. But the questions raised by black holes still return to us in other ways through mathematics, observation, and debates that have continued for decades. If the singularity is viewed only as an ending, the story becomes brief and absolute. But if it is viewed as a sign of a limit, it opens a path towards something deeper. And along that path, the next question is no longer only how far matter can be compressed, but whether anything that falls into a black hole leaves information behind for the universe. A small object falling toward a black hole may disappear from view very quietly. From far away, it does not explode in a brilliant burst of light, nor does it leave behind a clear streak like a meteor crossing Earth's atmosphere. The last light it emits is gradually stretched toward red, grows fainter, and then fades into the darkness surrounding the event horizon. To an outside observer, the story appears to end there. Something that once had its own shape, mass, temperature, structure, history, and position has entered a region from which no signal can return. It is no longer present in the directly observable picture of the outside universe. But in physics, no longer visible is not the same as no longer existing. A sealed box still contains whatever lies inside, even if no one outside can see it. A book placed inside a locked room still carries every line of text, every trace of ink, and every page. The question posed by a black hole is far deeper than one involving a box or a room, because the event horizon is not merely a wall that blocks our view. It is a boundary in space-time from which signals cannot return to the outside in the ordinary way. So when matter falls in, the question is not simply whether we can still observe it. The question is whether the information about it is still preserved somewhere in the universe. In physics, information does not refer only to messages, written words, or data stored in a computer. It means all the properties needed to describe the state of a physical system. The particles that make it up, their energy and motion, their arrangement, the relationships among its parts, and the details that make one object different from another. A hot cup of tea and a cold cup of tea contain different information. A quiet cloud of gas and a cloud spiraling into a black hole contain different information. A star before it collapses carries the history of the matter from which it formed. Yet when all of these things pass through the event horizon, the black hole, as seen from the outside, can be described by only a few quantities: its mass, electric charge, and rate of rotation. Most of the original detail appears to be hidden. That concealment alone is not yet a paradox. If a black hole were to exist forever, one could argue that the information remained inside, even though no one outside could ever retrieve it. It would be like a library locked behind a door that could never be opened. No one outside could read the books, but the books might still be there. The problem becomes deeper because Stephen Hawking showed that black holes may not be completely black. When quantum mechanics is considered near the event horizon, a black hole can emit an extremely faint form of radiation, now known as Hawking radiation. Over an unimaginably long period, it can gradually lose energy and mass, eventually evaporating away. This process is extraordinarily slow, almost entirely removed from human timescales. A stellar mass black hole would take so much longer than the current age of the universe to evaporate that the numbers become difficult to comprehend. Supermassive black holes at the centers of galaxies would last even longer. But in principle, if Hawking radiation is correct, a black hole is not a permanently sealed box. It is an object that can gradually disappear, and once the box is gone, the question becomes unavoidable. Where did the books inside it go? In its original description, Hawking radiation appears to be almost thermal. It depends mainly on the general properties of the black hole, and does not seem to carry all the detailed information about the matter that fell inside. Whether a black hole formed from a star, a cloud of gas, or some very different arrangement of matter with the same total mass, charge, and angular momentum, the radiation it later emits does not appear to recount those different histories in full. If the black hole evaporates completely and nothing else remains, the original information seems to have been erased from the outside universe. This conflicts with a deep principle of quantum mechanics. Information should not be completely destroyed during physical evolution. We can imagine a book being burned. In everyday life, once the flames have passed, we can no longer read it. Its pages have become ash, smoke, heat, and light. But at the microscopic level, according to physical principles, the information has not vanished absolutely. It has been dispersed into the motion of molecules, photons, hot gases, and the surrounding environment. In practice, reconstructing the book from its ash and smoke would be nearly impossible. But in principle, the final state remains connected to the initial one. A black hole makes this story far more troubling, because if it evaporates like a simple source of thermal radiation, the final state seems to lack the details needed to reconstruct what came before. This is the black hole information paradox. It is not a paradox in the sense of a clever puzzle, but a point of collision among three powerful ideas: general relativity, quantum mechanics, and the existence of the event horizon. General relativity says that once something passes beyond the event horizon, no signal can return. Quantum mechanics says that the evolution of information should not simply be erased. Hawking radiation suggests that a black hole can gradually lose mass and eventually cease to exist in its former state. When these three ideas are placed together, they create a question that is extraordinarily difficult to resolve. If the black hole disappears, where is the information it once swallowed? For decades, this question has opened many different paths of thought. Some proposals suggest that the information gradually escapes through Hawking radiation, but in a way far more subtle than the original thermal description implied. Other ideas suggest that information is encoded near the event horizon, as though the boundary of the black hole preserves an immensely complex record of everything that has fallen inside. Some approaches involve the holographic principle, in which the information contained within a region of space may be described on its boundary. Other models suggest that the final stage of a black hole could leave behind a tiny remnant, or lead to a deeper transition that classical general relativity cannot describe. Among these possibilities, the idea of a white hole emerges as one especially rich in imagery. If the interior of a black hole does not end at an absolute singularity, and if some quantum mechanism prevents the collapse from reaching infinity, then matter and information may not be erased. They may be preserved, transformed, or held in a state that cannot be observed directly from the outside. In the very distant future, if the black hole transitions into a white hole-like phase, what once went in might find a way to emerge again in some form. This remains a hypothesis, not evidence, but it shows why the question of white holes is not merely about reversing a black hole to create an elegant mathematical image. It is connected to a very serious problem: whether the universe preserves information. What makes this paradox especially well suited to black holes is their strange simplicity when viewed from the outside. An ordinary star contains an enormous amount of detail. It has a surface temperature, a chemical composition, a magnetic field, layers of gas, star spots, cycles of oscillation, a history of formation, and a surrounding environment. A planet is complex in a different way, with terrain, an atmosphere, oceans, a core, a magnetosphere, seasons, clouds, ice, and rock. But in the stable classical description, a black hole appears to erase nearly all of those details from its outward appearance. Two black holes with the same mass, charge, and rate of rotation would reveal almost nothing about what formed them. The universe seems to have compressed an immensely long story into only a few short numbers. That simplification was once captured in a famous phrase, "Black holes have no hair." The expression simply emphasizes that black holes do not retain the complex outward features seen in other celestial objects. But if every detail truly disappears from physical description, quantum physics does not accept that easily. A musical instrument and a chair could both be thrown into a black hole and both add to its mass, yet their microscopic states would not be the same. A star rich in hydrogen and a different collection of matter rich in heavy elements would carry different histories. If a black hole remembers only the total mass, total charge, and rate of rotation, where have all those subtle differences gone? Perhaps they are not lost. Perhaps they are encoded in a way too intricate for an outside observer to read with simple tools. Perhaps the event horizon is not a material surface, yet still acts as a place where information is recorded within the quantum structure of the black hole. Perhaps Hawking radiation, when understood more completely, is not entirely random, like a meaningless thermal mist, but carries extremely faint and difficult to detect correlations, like a piece of music stretched and blurred across an immense span of time. These possibilities belong to different areas of research, and not all of them require white holes, but they all arise from the same conviction. A black hole cannot simply be a cosmic trash bin where information is erased from reality. The slowness of black holes makes the paradox even more unusual. Hawking radiation from large black holes is far too weak for us to measure easily and directly. For the astronomical black holes known to humanity, the Hawking temperature is so low that it is almost completely lost within the background radiation of the universe. If a black hole is growing by consuming gas and dust or merging with other objects, the energy it loses through Hawking radiation is vastly smaller than the amount of matter it gains. The information paradox, then, is not something we observe as a clear explosion in the night sky. It is a problem of principle, a hairline fracture between enormously successful theories, yet one deep enough to change the way humanity thinks about reality. Within the quiet rooms of everyday life, information can seem fragile. A message is deleted, a sheet of paper is crumpled, a dream fades after waking. But at a deeper physical level, the question of information is not merely a question of human memory. It is a question about the continuity of nature. As the universe moves from one state to another, is there some fundamental thread connecting what came before with what follows? Or can that thread be completely severed in a special place, such as a black hole? Black holes make the question impossible to avoid because they conceal information, may eventually evaporate, and exist at the boundary between gravity and quantum physics. There is a quiet beauty in the way a region of darkness can give rise to so much intellectual light. From the outside, a black hole offers no answer. It sends no signal from beyond the event horizon. It does not open its deepest interior to a telescope. Yet that silence forces physicists to listen to other things. The consistency of the equations, the traces of gravitational waves, the light from heated matter nearby, and the deepest principles of quantum mechanics. The question of information does not arise from a desire to make black holes seem more mysterious. It arises from the effort to prevent the different parts of physics from contradicting one another. If information truly escapes through Hawking radiation, then the black hole does not destroy it, but merely hides it within extraordinarily subtle correlations. If information is stored at the event horizon, then that dark boundary may be more than the point of no return. It may also be where the universe remembers, in a way unlike any ordinary surface. If the information remains within a final remnant, then the death of a black hole is not a clean disappearance, but leaves behind a tiny fragment containing an immense history. And if a black hole transforms into a white hole, then what was once hidden may be given some form of return in the distant future. Each possibility carries its own difficulties, but all of them attempt to avoid one conclusion that seems too simple: that the universe allows information to be erased from reality without leaving any trace. Among these possibilities, the white hole holds a special place because it gives the question of information a clear direction. Inside a black hole, every future path slopes farther inward. A white hole, if it exists, would be a region from which everything can only emerge. If a black hole could somehow transform into a white hole, the process would be more than a strange event in space. It would suggest that what appeared to be lost had only been delayed, compressed, or carried through a phase that no outside observer could follow directly. A story that seemed to end at the event horizon might have another chapter, even if that chapter lies so far in the future that it is difficult to place within the imagination. Still, caution is essential. So far, there is no conclusive observational evidence that white holes exist, or that black holes truly transform into them. The information paradox also has many possible solutions that do not require a physical white hole to appear in the universe. Yet white holes bring the central issue into focus. A black hole is no longer viewed merely as the final destination of matter. It becomes a place where we test the meaning of conservation, the memory of the universe, and whether something that has entered the darkness may still leave a trace within the deepest structure of nature. When the previous part ended at the singularity, the question still followed the shape of collapse: how far matter could be compressed, where the equations ceased to work, and what theory might be needed to describe the deepest region. Here, the question turns slightly. It asks not only where matter goes, but what happens to the information carried by that matter. A leaf falling into a stream may vanish from sight, but the water still carries the motion it created. A star falling into a black hole may disappear from our telescopes, but physics must still ask whether its history has truly been erased, or merely rewritten in a language too deep for us to read. And from that question, the doorway toward white holes begins to come into clearer view, not as a certain answer, nor as a miracle that breaks the laws of nature, but as a possibility arising where familiar laws have not yet formed a complete picture. If a black hole preserves information, if the singularity is not an absolute ending, and if time inside and outside can diverge so greatly that a moment becomes billions of years, then the idea of a distant way out is no longer only an act of imagination. It becomes one of the ways physics asks whether the universe may someday return what has passed beyond its darkest horizon. If a black hole is a place where light can enter but never return, then its opposite seems almost as though it should not belong in nature at all. A region that nothing from the outside can enter, yet from which light and matter can emerge. A door that does not open inward, but only outward. A river that does not flow over a waterfall, but seems to rise from the bottom of the falls back toward the surface. This idea is called a white hole, and even its name carries a feeling of symmetry and disbelief. Yet the white hole did not first appear as a work of imagination. It emerged from the way the equations of general relativity can be read when the direction of time is reversed. In physics, some equations possess a very unusual kind of symmetry. If a process is described as valid when time moves forward, its time-reversed version may sometimes also be a mathematically valid solution. A film showing a ball falling to the ground and bouncing upward may look perfectly ordinary in one direction. Played backward, the ball rises from the ground along the same path and returns to the hand that released it. In many everyday processes, the reversed film looks unnatural because heat, friction, and disorder give time a clear direction. But within the fundamental equations, time symmetry can sometimes remain like a mathematical mirror, allowing a familiar image to cast a strange reflection. In certain theoretical descriptions, a white hole is the reflected image of a black hole. A black hole has an event horizon, beyond which every future path leads inward. A white hole would have the opposite kind of boundary. Nothing outside could pass into it, while anything within could only move outward. It resembles an inaccessible past rather than an inescapable future. A black hole hides whatever has fallen inside behind a dark horizon. A white hole, in the mathematical picture, appears to release something from a region into which no outside observer could previously have sent matter. This is precisely what makes it both fascinating and deeply uncomfortable to our intuition. It is important to understand that a white hole is not simply a black hole painted a brighter color. It is not a white object, a brilliant star, or a mouth visibly ejecting matter that telescopes have clearly observed. The word white is only used as a counterpart to black. A black hole is called black because light cannot escape from within its event horizon. A white hole is called white because, in the reversed model, matter and light may leave but cannot enter. The name makes the idea seem intuitive, but its true nature has nothing to do with color. It lies in the structure of spacetime and in the direction of the paths that are physically allowed. One way to picture this is to imagine two kinds of horizons. For a black hole, the event horizon is a boundary beyond which no signal can return. It cuts off the future of a falling object from the outside universe. For a white hole, the boundary works in reverse. An object outside cannot cross it to enter. If a black hole resembles a room with only an entrance, then a white hole resembles a room with only an exit. From the outside, the doorway allows no one to pass through, but from within, something may appear, move outward, and join the rest of the universe. This image makes a white hole seem like a mysterious source of emission. If one existed, it might release matter, light, or energy without any corresponding infall having first been observed from outside. This would be very different from most familiar astronomical phenomena. A star shines because nuclear fusion takes place in its core. A supernova shines because a star reaches the end of its life in a violent way. A quasar shines because matter falls toward the region around a supermassive black hole, releasing energy before being swallowed. In the case of a white hole, whatever comes out could not be explained by matter that had just fallen in from outside, because by definition, the outside cannot send matter into it. It would resemble an appearance rather than a process of accretion. That apparent emergence is one reason white holes face such difficulty when moving from mathematics into the real universe. A solution to an equation does not automatically become an astronomical object that nature can produce. Many mathematical structures are elegant and internally consistent under ideal conditions, yet difficult or impossible to sustain in a universe filled with disturbances, radiation, matter, collisions, and a clear thermodynamic direction of time. Classical white holes are generally considered unstable. Even a small amount of outside matter or radiation could disrupt their idealized structure. The real universe is not as quiet as an equation written on paper. It is always filled with microwave background radiation, dust, fields, gravitational waves, light from distant stars, and countless small disturbances. Another difficulty lies in the question of formation. Black holes have a more natural path into existence. A sufficiently massive star exhausts its fuel, its core can no longer resist gravity, collapse begins, and under the right conditions, a black hole forms. A white hole does not have an equally clear story unfolding in the familiar direction of time. If it is the time-reversed version of a black hole, it seems like an object that must already exist in the past, release matter, and then disappear, rather than form through a collapse that we might observe. This is why many physicists regard the classical white hole as more of a mathematical possibility than a celestial object waiting to be found through a telescope. Yet, its implausibility does not make the idea meaningless. In science, a theoretical structure that has not appeared in nature can still be valuable, because it reveals what the equations permit and where the limits of those possibilities lie. White holes help clarify the symmetries and asymmetries of black holes. They raise questions about the direction of time. They force us to distinguish between what mathematics allows and what physical nature can actually create. They also provide a language for thinking about deeper models, in which a white hole does not need to exist as a separate classical object, but may instead appear as the final phase of a black hole after quantum effects alter the picture of its interior. Here, the connection with the earlier parts of the story becomes natural. A classical black hole leads to a singularity. The singularity may be a sign that general relativity is missing its quantum component. The information paradox asks whether what falls inside is erased. Within this context, the white hole is no longer merely an elegant reversed image. It becomes one way of asking whether there may be some path outward, not in the sense of a spacecraft escaping from a black hole, but in the deeper sense of whether matter and information once hidden could return to the universe in another form at some very distant time. If we view a white hole as a film of a black hole played backward, its strangeness becomes immediately clear. An ordinary star does not naturally gather back all the light it has emitted and return to an earlier state. A shattered glass does not spontaneously collect its fragments from the floor, lift them onto the table, and become whole again. A cloud of smoke does not naturally contract into an unburned match. The world around us has a clear arrow of time because entropy, or the degree of disorder, tends to increase. A classical white hole seems to run against that intuition. It resembles an event arranged with extraordinary precision, in which every initial condition must be tuned to an unrealistic degree. Even the smallest deviation could cause the entire order to collapse. But white holes in modern models of quantum black holes do not necessarily have to be classical objects that have existed since the beginning of the universe. Some ideas suggest that a white hole could be the final result of a collapse. Matter falls inward, forms a black hole, and reaches an extreme region. Then, instead of encountering an infinite singularity, it passes through a quantum phase. Much later, very much later, from the perspective of an outside observer, that phase might appear as a white hole. In this view, the white hole is not created from nothing. It is the late, profoundly late stage of the black hole's story. The distinction between these two ways of looking at white holes is extremely important. A classical white hole, existing independently as the perfect time-reversed counterpart of a black hole, faces serious problems of stability and formation. A white hole appearing as the final phase of a quantum black hole belongs to a different kind of question. It does not require the universe to have created a fully formed white hole in the distant past. It requires only that the collapse inside a black hole does not continue to infinity, and that time outside is stretched so greatly that the transition appears extremely late. This remains a hypothesis, but it brings us closer to the central question: could a black hole become a white hole? If physics contains an answer, it is unlikely to be as simple as flipping a switch from black to white. A black hole would not suddenly light up like a star being turned on. Any transition would involve the deepest structure of spacetime, the limits of gravitational collapse, the way information is preserved, and the difference between time inside and time outside. From far away, throughout most of the history of the universe, the black hole might continue to look perfectly ordinary. Only at an extremely late stage, after its mass had decreased or after some internal quantum process had reached a critical threshold, might a white hole-like phase appear in certain models. We might picture this as a seed lying deep beneath the ground for a very long time. From above, the soil appears still. No one can see the subtle changes unfolding in the darkness. The moisture shifts, the outer shell softens, and the inner structure slowly begins to move. Then, at a certain moment, a shoot appears above the surface. To someone who sees only that instant, it may seem to have emerged suddenly from the earth. But the story actually began much earlier, in a hidden region below. If a black hole can become a white hole, the final appearance of matter or radiation may likewise be only the late visible surface of a story that has long been unfolding behind the event horizon. Even so, we should not let this image make white holes seem too easy. The growth of a seed is a biological process observed countless times. A white hole is not. No telescope, has yet confirmed an object that must unquestionably be identified as a white hole. High-energy explosions, gamma-ray sources, fast radio bursts, and brief flashes of light in the universe all have many possible astronomical explanations, most of which do not require white holes. The appeal of an idea cannot replace evidence. In science, the stranger a possibility is, the more rigorously it must be tested. Even so, the white hole retains a special value in this journey. It allows the question of the black hole to be turned around. Instead of asking only why nothing can escape, we can ask what physics would look like in a region that nothing can enter. Instead of asking only how matter is hidden, we can ask whether that concealment could ever end. Instead of viewing the event horizon only as the boundary of loss, we can consider it as part of a larger structure in which past, future, and observability are no longer arranged according to familiar intuition. In the classical picture, a white hole resembles a waterfall flowing backward, an object emerging from darkness without any history of matter falling into it from outside. In the more modern quantum picture, it may resemble the delayed exit of a black hole that has existed for an immense span of time. These two images are not exactly the same, but both touch the same mysterious region, whether spacetime can allow collapse to reverse. That question cannot be answered through everyday intuition. It requires mathematics, observation, and a deeper theory of gravity at the quantum scale. A white hole that exists only on paper would still be a useful mirror. It reflects the black hole in reverse and makes clearer what gives a black hole its unusual nature. A white hole that truly existed in the universe would be one of the most transformative discoveries in humanity's understanding of spacetime. And if a black hole could genuinely become a white hole, it would join two seemingly opposite images into a single story: collapse and rebound, concealment and emergence, darkness and a form of light arriving unimaginably late. At the edge of this line of thought, the white hole remains an unconfirmed possibility. It is not a ready-made answer, but neither is it merely a decorative counterpart to the black hole. It stands precisely where several great questions meet. General relativity permits strange structures of spacetime. Quantum mechanics does not easily accept the destruction of information, and black holes carry everything into a region that direct observation cannot follow. From here, the question is no longer simply what a white hole is. It becomes something deeper. Through what mechanism could a region that was once a black hole ever reach such an opposite state? In a very distant sky, among countless sources of light already given names, a strange signal may once have passed unnoticed by humanity. It would not need to appear as a brilliant white sphere, nor remain fixed in space, like a newly born star. If white holes exist, their signs would likely be far subtler and more difficult to interpret than the name suggests. White does not refer to color, but to the reverse direction of a structure. A black hole hides light beyond its event horizon. A white hole, in the theoretical picture, allows something to emerge from a region that the outside cannot enter. A telescope might not see a white hole as a complete object. It might record only a brief flash, an unusual brightening, or a burst of energy arriving from a place that previously showed no obvious activity. That light may have traveled for millions or billions of years before reaching the telescope's mirror. By the time it is recorded, the event has already been over for an immense span of time. On a data screen, all that remains may be a curve that rises and fades, a trace of energy in gamma rays, X-rays, radio waves, or some other part of the spectrum that human eyes cannot see directly. But the universe is not lacking in strange flashes. A massive star can blaze as it dies in a supernova. Two neutron stars can collide and release tremendous energy, sending light and gravitational waves across space. Hot gas spiraling around a supermassive black hole can make the center of a galaxy shine more brightly than billions of stars. Gamma-ray bursts may appear for only a few seconds and then vanish, leaving questions in the data that last for years. The sky is not silent in any simple sense. It is always filled with brief echoes, passing points of light, and events that flare for only a moment before fading back into the darkness. For that reason, any signal resembling a white hole would have to quietly survive many more familiar explanations. A powerful flash would not be enough. A vast release of energy would not be enough. A short-lived event would not be enough. Astronomers would study the color of the light, the way it brightened, the way it faded, the surrounding galactic environment, the elements that might appear in its spectrum, and whether any other signals accompanied it. If gravitational waves were present, the story might point toward a collision between compact objects. If there were signs of stellar gas being thrown outward, it could mark the death of a star. If an obvious source of infalling matter were present, it might be connected to an accreting black hole. For a white hole to move beyond the page, it would need to leave a more distinctive trace. We might imagine the sky's data as a vast snow-covered field at night. Across it are countless familiar tracks, the marks of dying stars, active galaxies, collisions, and matter heated as it falls into an intense gravitational field. A new track becomes interesting only when it does not quite match the known paths. It does not need to be loud. It only needs to remain different in a consistent way. A brightness that fades in the wrong pattern. Energy appearing without a familiar source to power it. An event too brief, too clean, or too unusual for ordinary explanations to cover completely. Even then, strangeness is not evidence. In astronomy, an unexplained signal does not automatically become a new kind of object. Many phenomena once seemed mysterious before being explained by known but rarer processes, or by better data. Sometimes, dust dims the light. Sometimes the distance has been estimated incorrectly. Sometimes, an event that appears isolated is actually part of a more complicated environment. Sometimes different instruments only need to observe it once more, at another wavelength, for the story to become more ordinary. The universe has no difficulty misleading us with things that are entirely real, yet only partly understood. A white hole, then, would not be easy to recognize. If it existed only as a very brief phase, it might vanish before telescopes had time to turn toward it. If it emitted most strongly in a difficult-to-observe wavelength, much of its energy could pass unnoticed by human eyes and many instruments. If it were very small, the signal might be weak and lost within the background noise of the universe. If it were extremely distant, the expansion of space could stretch and redden its light before it reached Earth. A bell ringing at the end of an immense hallway may reach us as only a thin note, almost impossible to separate from the sound of the wind. In classical models, a white hole would also struggle to survive for long in the real universe. Outer space is not completely empty. There is always background radiation, dust, light from distant stars, gravitational fields, and small disturbances passing through. A structure that allows everything to leave but nothing to enter would have difficulty preserving its perfection once the outside world touched it. Even a tiny amount of matter or radiation could destabilize the idealized picture. So, if white holes are real, they are unlikely to resemble stable stars shining quietly for billions of years. They may be more like a moment, a transitional phase, or the final echo of some deeper process. The more compelling path lies in the possibility that a white hole does not appear on its own from nothing, but instead emerges as the late stage of a black hole. In this picture, a star collapses and forms a black hole, holding matter and information beyond the event horizon for an immense span of time from the perspective of the outside universe. In the deepest region, where classical general relativity leads to a singularity, quantum effects may prevent the collapse from continuing to infinity. The compression reaches some limit, and then the story inside changes direction. From the outside, that process may be stretched across enormous intervals of time. At some very distant moment, what had been hidden may appear as a kind of release, not because matter has just fallen in, but because an ancient story has finally found a way out. A white hole of this kind, if one has ever appeared, might not resemble a living star. It could look more like delayed light, a sudden release of energy, or a brief fracture in the familiar order of astronomical sources. It might also leave very little evidence behind, depending on the original mass, the lifetime of the black hole, and the quantum mechanism within it. For large black holes, the waiting time could extend far beyond the present age of the universe. For very small black holes, if any were created in the early universe, speculative models allow for shorter timescales. Though all of this remains unconfirmed, the sky may have preserved signals like these, or it may never have produced them at all. This difficulty does not make the question any less meaningful. It only makes the question more subtle. A white hole is no longer something to search for by simply looking for the brightest point in the sky. It becomes a pattern to recognize in the way energy appears, in the way light fades, in whether an event has a familiar source of fuel, and in the faint correlations among different kinds of signals. Modern astronomy does not listen to the universe through only one sense. It uses visible light, X-rays, gamma rays, radio waves, neutrinos, and gravitational waves, with each one carrying a different part of the story. A strange event gains real significance only when several of those parts begin to fit together. On some nights, a telescope sweeps across the sky and records thousands of small changes. A variable star brightens slightly. The active core of a distant galaxy grows stronger. An explosion begins long before its light reaches Earth. Most of these changes will eventually be placed within known categories. A few remaining signals will stay on a waiting list, observed again, compared again, and tested again. It is there that new hypotheses can survive cautiously. No grand announcement is needed. Only a mismatch persistent enough to make older models give way to a different question. If a white hole leaves a signature, it would likely enter science in this same gradual way. Not through a moment when the whole world looks up and sees a white doorway opening among the stars. Perhaps it would begin with an unusual dataset, followed by a cautious paper, then independent observations, and then the slow elimination of competing models. One day, if no familiar explanation can account for a certain kind of signal, and if a white hole model explains it more successfully without violating what is already known, the idea may advance one step further. Science often enters new territory through footprints that small. Until then, the white hole remains as the reverse shadow of the black hole. It has no secure place on the established map of astronomy, but it does have a place among questions about spacetime. It turns the black hole from merely a place of entry into a question about an exit. It makes the event horizon more than a boundary of silence, suggesting that it could be the beginning of a story far longer than the lives of stars. And it allows every unfamiliar flash in the data, even if it is eventually explained by something else, to remind us that the universe does not always reveal its deepest structures through clear and obvious images. So if a white hole exists, it may look nothing like what the imagination expects. It may not be white, round, stable, long-lived, or easy to distinguish from countless other cosmic outbursts. It may be only a moment when space-time returns something that has been hidden for far too long. A strange flash in the darkness. A burst of energy with no obvious source flowing inward. A delayed echo from the center of a black hole that has already passed through the longest part of its life. And even that image remains only a possibility until the universe leaves behind a trace clear enough for humanity to read. From those possible traces, the story quietly turns inward once more. If a white hole is unlikely to survive as an independent object, then the deeper question lies in the mechanism that might produce one from a black hole. Matter falls in, the event horizon closes behind it, time stretches, and the classical singularity appears as the boundary of the theory. Then, in the deepest region, some quantum effect may alter the direction of collapse. Not a bright doorway opening at once, but a process unfolding very slowly for the outside universe. The black hole as a long-lived state of compression. The white hole as a delayed way out. Between those two images lies the idea that will carry us forward. The rebound of space-time. In the deepest interior of a black hole, classical general relativity draws a path that continues endlessly downward. Matter crosses the event horizon and keeps falling through a region where every possible direction into the future slopes inward, until it reaches what the equations call a singularity. But that singularity is not a place anyone has observed, nor is it a surface that a telescope could photograph. It is an extreme signal from a theory being pushed to its limit. As density and curvature approach infinity, the picture no longer resembles a complete answer. It begins to look more like a dark region on a map, where familiar paths curl inward and become a profound question mark. In some approaches to quantum gravity, that collapse may not continue all the way to infinity. When matter is compressed to an extremely small scale, spacetime may no longer remain smooth and continuous as it does in the classical description. Quantum fluctuations in geometry itself may begin to matter. At that depth, gravity may no longer be only the gentle curvature of spacetime, but may reveal limits, discrete structures, or effects that never appear on larger scales. The collapsing matter may encounter a threshold that the classical equations do not know how to describe. The closest image is not an immediate explosion, but compression reaching its limit. A ball pushed deeper and deeper beneath the surface of the water experiences increasing pressure. From above, it disappears from view, and the surface closes as though nothing has happened. But below, the ball cannot be compressed forever. Its material, the surrounding pressure, and its internal structure together create a limit. At some point, if the force holding it down is removed or the balance shifts, it may rebound toward the surface. That rebound does not erase the compression that came before. It is the next part of the same story, unfolding only after everything has been pushed to its limit. For a black hole, this is only an analogy, but it opens the way to an important idea: the black hole bounce. In some models, infalling matter is not crushed into an infinite singularity. Instead, when it reaches an enormous density, quantum effects of gravity may create a kind of pressure or phase transition that stops the collapse and reverses its direction. The core no longer continues downward in the classical sense. It passes through a region that general relativity alone cannot describe, then enters a new phase in which what once fell inward may find a path outward. This rebound has not been observed as a physical fact. It is not something visible in an image of a black hole, nor is it a conclusion accepted by every physicist. It is a possibility that appears in models attempting to bring general relativity and quantum mechanics together. Yet the idea is compelling because it addresses several fractures in the classical picture at once. It avoids an infinite singularity, it offers a new way to think about information, and it allows the story inside a black hole to continue without completely overturning what is already known about the event horizon outside. One of the most striking concepts within this line of thought is the Planck star. The name does not describe a star in the ordinary sense, and certainly not a sphere of gas-burning fuel like the sundae. It refers to an extremely compressed state in which matter inside a black hole reaches a density near the Planck scale, the realm where quantum effects of gravity may become decisive. There, space and time may no longer behave like a smooth background. They may resemble a fabric that looks perfectly fine from a distance, but reveals an extremely small underlying structure when magnified to its deepest level, preventing unlimited compression toward infinity. If such a Planck star formed inside a black hole, it might exist for only a very brief time, according to the clock of the interior. But for an observer outside, the story would be very different. Extreme gravity stretches time. Light and signals leaving the region near the event horizon are reddened, weakened, and slowed in the eyes of someone far away. A process that unfolds quickly inside may correspond to an immense span of time outside. The black hole could therefore appear to remain quietly in place for billions of years, even though in its deepest interior, the collapse may already have reached its limit and entered another phase. This difference in time makes the idea of a rebound especially strange. It is not like a bomb exploding the moment a star collapses. It is more like an instant buried beneath gravity. then stretched in the view of the outside universe until it appears almost motionless. Inside, matter may pass through a transitional region. Outside, galaxies continue to turn. Generations of stars are born and die. The background glow of the universe gradually cools, and the black hole remains as a dark point, only after an unimaginably distant span of time. If the model is correct, might that deeply compressed region emerge as a white hole phase. The difference between this picture and the classical white hole lies in its origin. A classical white hole resembles an object that must already be built into the structure of the universe, a perfect time-reversed shadow of a black hole evolving in a direction that nature does not easily produce. A white hole formed after a rebound has a clearer past: the collapse of a star, the formation of an event horizon, the inward fall of matter, extreme compression, and finally a quantum phase. It is not like a waterfall that has flowed backward from the beginning. It is more like water that has descended into a deep basin, reached a bottom it cannot penetrate, and then found another way out after an immense delay. In this picture, the black hole and the white hole are no longer entirely separate objects. They may be two phases of a single structure. The first phase conceals, preserves, and compresses. The second opens, releases, and returns what was hidden in another form. Between them lies no simple mechanical hinge, but a region where spacetime must be described through deeper physics. Familiar ideas such as inside and outside, before and after, may become difficult to separate. A black hole would not become a white hole in the way an object changes color. It might pass through a transformation in the causal structure of spacetime itself. These models still contain many unanswered questions. The rebound must be stable enough not to collapse the moment it appears. The information that fell inward must somehow be preserved. The energy released during the final phase must take a form allowed by the laws of physics. The transition time cannot be chosen arbitrarily, because it must remain consistent with the black hole's mass, Hawking radiation, and everything telescopes have not observed. Each condition acts like a slender thread tying the model to reality, preventing the idea from drifting too far from observational science. A gentler version of this picture is to imagine a black hole as an extreme storage region of the universe. Whatever falls inside can no longer send signals back and is no longer present to the outside world in the familiar way. Yet it may not be erased from reality immediately. It is carried into a realm where time, gravity, and quantum physics work together in ways that remain unclear. If a rebound occurs, that region does not preserve everything forever. It holds what has fallen inside for an extraordinarily long time from the outside perspective, until one day, when the conditions of the model are met, the compressed contents may be released in the outward direction of a white hole. That release would not mean that the original objects emerge intact. A chair, a stone, or the outer gas of a star would not return in the same form it had before falling in. At such extreme densities and energies, the familiar structure of matter would have been destroyed long before. Whatever emerged might take the form of radiation, particles, energy, or physical states, very different from the original objects. Information, if preserved, could also be encoded in an extraordinarily subtle way, rather than stored as a simple record. A story crushed into fragments and rewritten in the language of quantum physics would no longer read like the original book, even if it still carried traces of its earlier history in principle. The white hole in this idea does not promise that everything lost will return exactly as it was. It only suggests that an absolute endpoint may not be nature's only option. A black hole may be an immensely long process in which matter enters a region we cannot follow, while at the deepest level, the collapse never reaches infinity. Darkness does not necessarily mean erasure. It may be a state of waiting, extended across ages that no living observer could ever witness in full. That waiting belongs to the unique timescales of black holes. Stellar mass black holes may survive far longer than the stars that gave birth to them. Supermassive black holes at the centers of galaxies may endure through eras when even the final stars have gone dark. If the transition into a white hole depends on mass and quantum effects, many black holes may still be in the earliest stage of their story from the perspective of the universe. They look like endings, but in the rebound model, they may be only profoundly dark seeds, waiting for a season that does not belong to the present age. Outside a black hole, the universe continues moving to its own vast rhythm. Stars are born within cold clouds of gas, shine for millions or billions of years, and then fade in different ways. Galaxies turn slowly through the darkness, carrying dust, gas, old stars, young stars, and regions of space that are almost entirely empty. Light crosses immense distances, stretched by the expansion of the universe, before arriving somewhere far away after a journey longer than any human memory. Meanwhile, a black hole may remain within that landscape as an enduring region of darkness, almost unchanged across spans of time in which everything around it has already become history. That stillness may conceal a profound difference between time in the outside universe and time near a region of extremely strong gravity. From far away, every signal emitted close to the event horizon appears slowed, reddened, and weakened. A pulse of light sent from very near the black hole may arrive later, fainter, and more stretched out than it was when it began. The closer it comes to the boundary of no return, the greater the difference becomes. To a distant observer, the fall into a black hole seems to be drawn out, like a quiet sound echoing through a hallway that grows deeper and deeper, until it becomes almost impossible to distinguish from silence. But for the object that is falling, its own time does not have to stretch in the same way. An imaginary clock traveling with it continues ticking according to its own rhythm. It does not feel each second being drawn into centuries. The difference appears only when two clocks in regions of different gravitational strength are compared. One far from the black hole, where spacetime is relatively flat, and another deep within the strong gravitational field, where every signal trying to escape must pass through an immense curvature. The two clocks no longer tell the same story about the distance between two moments. Here, the idea of a black hole becoming a white hole begins to take on a rhythm of time all its own. If some quantum process inside the black hole prevents the collapse from reaching a singularity, that process may unfold within a finite interval according to the clock of the interior. It may resemble a moment of compression reaching its limit and then reversing direction. But for the outside universe, the extreme gravitational field may stretch that moment until it becomes almost impossible to perceive. A brief motion in the deepest region could correspond to a wait lasting billions of years, or far longer, outside. This picture does not resemble an explosion occurring immediately after a star collapses. A star may die, its core contract, and a black hole form, while to the surrounding universe, that dark region continues to exist through many later generations of stars. New clouds of gas give birth to new suns. Planets slowly cool around distant stars. Smaller galaxies fall into larger ones. The background glow left over from the early universe continues to fade and cool. Throughout all that time, any phase transition deep inside the black hole may remain hidden from the outside by gravitational time dilation and by the event horizon itself. A gentler way to picture this is to imagine a room buried far beneath the ground, where a lamp goes dark for only a moment. To someone inside the room, the darkness lasts only briefly, but the signal reporting that the light has gone out must travel through long corridors, heavy doors, and transmission lines that slow it down before finally reaching the surface. By the time someone above receives the message, the outside world has passed through a very different span of time. The comparison is not perfect because a black hole is not a building with actual hallways, but it preserves the essential idea. A local event and the time assigned to that event by a distant observer can differ so greatly that they seem to belong to two different cosmic rhythms. In rebound models, This difference allows a black hole to appear stable for an immense period, even if its interior does not end in an infinite singularity. The black hole does not need to open immediately. A white hole does not need to appear the moment the star collapses. The internal process, if it exists, may be completed quickly according to the clock of the deepest region, while its outward expression appears only in a very distant future. In this sense, a black hole resembles a delayed state of spacetime, where something that has already happened inside is not the same as something the outside universe has already been allowed to see. This changes the feeling of a black hole. It is not merely a place that holds matter inside. In a relative sense, it may also be a place that holds time. Whatever falls in can no longer send a signal outward, and profound changes in the interior cannot easily reveal themselves at once. Seen from far away, a black hole seems to stretch the final moment of collapse across enormous ages. Meanwhile, deeper within, physics may already have crossed a threshold that light in the outside universe has never been permitted to describe. For larger black holes, the difference in time becomes even harder to imagine. Even stellar mass black holes may survive vastly longer than the current age of the universe, if we consider Hawking evaporation alone. Supermassive black holes at the centers of galaxies would endure even longer, like dark islands lying in the deepest reaches of cosmic time. If the transition into a white hole phase depends on mass, the largest black holes may have to wait through eras beyond the age of shining stars. They could remain after many galaxies have exhausted their gas, after new stars can no longer form easily, and after the universe has become far colder and emptier than it is today. Such timescales make the white holes seem less like a brilliant spectacle in the present-day sky, and more like a story belonging to the deep future. Most of the black holes humanity can observe may still be very young compared with their potential lifetimes. A black hole formed by the collapse of a massive star may already have existed for millions or billions of years, yet on the timescale of a hypothetical quantum process, that may be only the beginning. Its center may already have passed through something according to its own clock, while the outside universe has not yet reached the moment when that change becomes visible. There is a particular stillness in this possibility. The black hole no longer evokes only images of swallowing and endings. It becomes an object of waiting, a dark point whose interior and exterior do not share the same rhythm of time. A place where the story may already have turned a page in its deepest layers, while the book's outer cover remains closed before every observer. If a white hole eventually appears, it may not be the immediate reversal of a collapse, but the delayed return of a process hidden beneath gravity for spans of time so vast that the imagination can follow only very slowly. This delay also helps explain why the absence of observed white holes does not immediately prove the idea wrong. A process may be real yet too rare, too distant, too faint, or destined for an age that has not yet arrived. Many phenomena in the universe become observable only when technology, timing, and theory finally meet. Gravitational waves passed through Earth long before humanity built instruments sensitive enough to record them. Exoplanets orbited other stars for billions of years before telescopes learned to recognize the tiny dimming produced as they crossed in front of their suns. A signal connected to a white hole, if such a signal exists, may likewise belong to a class of traces that humanity will need a long time to learn how to recognize. Even so, caution remains essential. A timescale that is too long can make an idea difficult to test. A process that unfolds only after trillions upon trillions of years is not easy to distinguish, within present-day observation, from something that never occurs at all. Models must offer consequences that can be searched for, even indirectly. A particular form of radiation, a small remnant, a trace left by a primordial black hole, or some limit on the way black holes evaporate. Without any testable signature, the idea would remain closer to philosophy than to experimental astronomy. Science may dream across immense distances, but it still needs a thread connecting that dream to data. The difference between time inside and outside also makes the phrase become more subtle. In everyday life, When one thing becomes another, the process can usually be followed from beginning to end. Water freezes, wood burns into ash, and a seed grows into a young stem. We can watch the stages unfold according to a relatively shared rhythm. With a black hole, the process cannot be placed so easily on a single timeline. A phase transition may occur inside, while outside, observers see only a black hole enduring for an immense span of time. The white hole phase, if it appears, may arrive only after a wait that no observer living in the present era could ever follow in full. In rebound models, then, the black hole and the white hole resemble two sides of a story stretched by gravity. The first side is collapse. A star loses its ability to support itself, matter falls inward, and an event horizon forms. The second is delayed release. The extreme interior does not continue toward infinity. The process changes direction, and some form of white hole appears in the distant future. Between those two sides lies a span of time that does not pass uniformly for every observer. There is no single cosmic clock hanging outside the universe, declaring that everything must unfold at the same pace. This picture also carries the question of information into a deeper dimension of time. If information is not destroyed, it does not necessarily have to return quickly. It may be encoded in the state of the black hole, gradually dispersed through Hawking radiation, or, in some models, held until a very late transition phase. A locked library is difficult to read, not only because its door is closed, but because the key may not appear until another age. The outside universe may have to wait far longer than the rhythm of the interior process before any trace becomes observable. In this possibility, a white hole is not a denial of the black hole, but a state that may lie at the far end of its lifetime. The black hole still has an event horizon. Light still cannot escape from within it in the ordinary way. Falling matter still disappears from the view of the outside universe. Everything already known retains its place in the present era of observation. The new element lies only in the very late story, when classical collapse is no longer assumed to continue endlessly toward infinity, and quantum gravity may open another path of evolution. A small black hole, if one formed in the early universe, may bring these ideas somewhat closer to observation. Because lower mass may correspond to shorter evaporation or transition times in some models, remnants or flashes of energy from such black holes are sometimes considered in observational searches. But primordial black holes themselves have not yet been conclusively confirmed as a directly observed population. They occupy a region where early universe cosmology, dark matter, high-energy radiation, and quantum gravity meet. Every step in that region requires a careful distinction between possibility, model, and evidence. For larger black holes, especially supermassive ones, the story belongs almost entirely to a future beyond the reach of every familiar structure that exists today. These objects may endure after ordinary stars have faded, after galaxies no longer shine as they do now, and after the universe has become far colder and darker. If they ever enter a white hole phase, it would be an event in a vastly older universe, beneath a sky unlike anything humanity has ever seen. In that setting, a flash from a white hole would be more than a burst of energy. It would be the echo of a star that died in a past too remote to measure in the scale of living things. That remoteness may make the idea feel uncertain, but it also suits the nature of black holes. Black holes have always been objects of limits. The limit of light, the limit of time, the limit of theory, and the limit of observation. Adding a white hole to the end of the story extends those limits farther into the future. The universe is no longer viewed only through what happens during the age of shining stars, but also through possibilities belonging to much later eras, when physics continues operating through a silence longer than all biological history. At a deeper level, this brings our attention back to a principle that has been present since the beginning of the journey. Time does not pass in the same way everywhere. Near a black hole, time bends together with space. In quantum models, That difference may become the bridge between a brief process inside and an immense weight outside. 1 second in the deepest region does not necessarily correspond to 1 second in distant galaxies. A small quantum motion may be stretched across the history of the universe. A rebound may not be an event of the present, but the seed of a faraway future. A black hole, then, does not keep its secrets through darkness alone. It keeps them through time. Between the inside and the outside, it places not only a boundary that light cannot cross, but also an enormous difference in the rhythm of events. If a white hole lies at the end of that path, it would not appear as a quick answer to everything that fell inside. It would resemble a very late echo, emerging from a place where light once could not return, after the deepest structure of spacetime had passed through a transformation that classical physics could never fully describe. From the idea of 1 second inside and billions of years outside, the story begins to expand beyond black holes alone. It touches a larger question about the universe as a whole. Could an immense outward eruption ever be understood as the opposite face of a collapse somewhere else? That association naturally leads toward the Big Bang, the moment when the space, time, matter, and energy of the observable universe emerged from an extremely hot and dense state. But the Big Bang and a white hole share similarities that are intriguing enough to invite comparison, while also differing in ways so profound that they must be explored very slowly. When a white hole is imagined as a place from which matter and light emerge, it is easy for the mind to drift toward the Big Bang. One is a theoretical region that allows everything to move outward. The other is the hot, dense beginning, when the observable universe existed in an extreme state before expanding into the vast space we know today. Both suggest a kind of opening. Both draw our thoughts toward a very deep past, when familiar structures such as stars, planets, and galaxies did not yet exist. But that resemblance is only the first layer. When we look more closely, the Big Bang and a white hole cannot be placed side by side too quickly. The Big Bang is often imagined as an explosion occurring at some point within empty space. That image is very common, but it is not accurate. In modern cosmology, the Big Bang was not a fireball exploding inside a pre-existing room of space. It describes the extremely hot and dense state of the early universe, followed by the expansion of space itself. There was no single center in space where the explosion began and from which matter flew outward in every direction. Every region of space was once much closer to every other region, and as the universe expanded, the distances between galaxies grew, much like points on the surface of an inflating balloon. The balloon is also only an analogy, but it helps correct an important misunderstanding. If small dots are drawn on the surface of a balloon and the balloon is inflated, each dot will see the others moving farther away. No point on that surface is the center of the expansion. The center of the balloon lies within the three-dimensional space beyond its surface, but imaginary beings living on that two-dimensional surface would not need that center to describe the expansion of their world. Our universe is far more complex, but the central idea remains gently similar. The Big Bang was not matter expanding into space. It was the space between regions of matter growing larger. A white hole, by contrast, is classically understood as a structure within space-time. It has a special causal boundary with an outside and an inside in the geometric sense, and a direction that matter cannot cross from the exterior. However strange it may be, it resembles an event or a region within the universe more than it resembles the universe as a whole. If a white hole releases matter, that matter emerges into an already existing surrounding spacetime. The Big Bang is not so simple. It did not release the universe into an empty stage. It was the opening of the stage itself. This difference makes the statement, "The Big Bang was a white hole," far too simple. It is visually suggestive, but it can easily distort the science. The Big Bang has no observable outside in the ordinary sense, where someone might stand and watch matter rush outward. There is no edge of the explosion that we can point to and say, "This is where the universe began within space." As telescopes look farther away, They do not see the center of an explosion. They see the universe at increasingly earlier times, because the light has traveled immense distances before reaching us. The cosmic microwave background, the ancient light left from the time when the universe became transparent, arrives almost uniformly from every direction, like a distant warm mist surrounding our entire field of view, rather than coming from a single point. Still, the connection between the Big Bang and a white hole is not entirely meaningless. Both touch the same broader problem. What happens when general relativity leads us toward an extreme state? In a black hole, the singularity lies in the future of anything falling inward. In the case of the Big Bang, if the expansion of the universe is traced backward, the classical equations lead toward a state so hot and dense that a singularity may appear in the past. In both cases, familiar physics is pushed to its limits. In both, quantum gravity may become necessary. And in both, words such as beginning or ending may simply reflect the limits of a theory that is not yet deep enough. Some speculative models suggest that our universe may be connected to the interior of a black hole in another universe, or that a collapse somewhere else could lead to an expansion resembling the birth of a new universe. These ideas are compelling because they turn the boundary between black holes, white holes, and cosmology into a more continuous story. A black hole in one region might, in theory, connect to an expanding region elsewhere. An extreme collapse might not end in infinity, but instead open into a new phase of spacetime. Yet this remains a deeply hypothetical area without conclusive observational evidence. It is not part of the firmly established foundation of the standard Big Bang model. The standard Big Bang model does not say that the universe emerged from a confirmed white hole. It describes a universe that was once hotter and denser, then expanded and gradually cooled. From the early hot plasma, light particles formed, followed by light atomic nuclei. After hundreds of thousands of years, electrons joined with nuclei, allowing light to travel freely. That ancient light is now observed as the cosmic microwave background. Much later, gravity drew slightly denser regions together, forming stars, galaxies, galaxy clusters, and the vast cosmic web. This picture is supported by many kinds of observations, including the expansion of the universe, the abundance of light elements, and the cosmic microwave background. None of this takes away from the beauty of the question about white holes. It simply places the idea at the proper distance. The Big Bang is the story of the entire observable universe. A white hole is a theoretical structure within space-time, or, in deeper models, a possible reverse phase of a black hole. The two images may touch in the extreme regions of physics, but they should not be blended into a single answer. Saying that the Big Bang resembles a white hole, because both involve an emergence from an extreme state, can be a useful comparison. Saying that the Big Bang has been proven to be a white hole goes far beyond what science currently knows. A gentle way to preserve this distinction is to imagine two scenes. In the first, a room already exists, and at its center is a doorway that allows something to emerge but nothing to enter. No matter how strange the doorway may be, the room remains the environment surrounding it. This is closer to the image of a white hole as a region within space-time. In the second scene, there is no room in which an explosion takes place. Instead, the distance between every point in the room is increasing. The walls, the floor, the ceiling, the measuring tools, and every empty interval are all part of that expansion. This is closer to the cosmological picture of the Big Bang. The difference also appears in the direction of observation. A white hole, if it were an object or event within the universe, might leave a local signature, a flash of light, unusual radiation, or a release of energy from a particular region of the sky. The Big Bang left traces in every direction. It is not an event located at some distant coordinate, but the shared past of all observable space. When we look at the cosmic microwave background, we are not looking toward the center of an explosion. We are looking back to the ancient era when light first escaped the hot, dense matter of the early universe. That light surrounds our view because it belongs to the entire young universe, not to a single object within it. Even so, both ideas lead toward a deeper sense of time. A white hole, if it emerges from a black hole, may be the late chapter of a collapse stretched by gravity. The Big Bang is the earliest chapter that modern cosmology can trace with reliable evidence. One lies in the unimaginably distant future of a dark object. The other lies in the unimaginably distant past of the entire observable universe. Both bring us to boundaries where questions like what came before or what comes after can no longer be answered easily through the images of everyday life. Inside a black hole, the question of what comes after is hidden by the event horizon. Matter falls inward, no signal returns, and classical relativity leads toward a singularity. With the Big Bang, the question of what came before is equally complicated. If time as we understand it is part of the expanding universe itself, then asking what happened before the Big Bang may not be like asking what happened before an ordinary event in time. Some models allow for an earlier phase, a cosmic bounce, or a parent universe. Others treat the Big Bang as the boundary of the classical description, where the word before requires a deeper theory before it can have a clear meaning. Here, the resemblance to a black hole becomes very subtle. In both cases, the classical equations carry us toward a region where time itself may lose its familiar meaning. At the center of a black hole, moving forward is no longer like crossing a room. At the Big Bang, before is no longer like turning back one more day on a calendar. Spacetime is not a fixed container holding every event. It is part of the story. When the story is pushed to an extreme, the container itself is transformed, and familiar questions must be asked more carefully. Models that describe the Big Bang as a kind of enormous white hole are appealing because they offer an intuitive image. The universe is something emerging from a region that cannot be entered, but that image can obscure important differences. A white hole has a horizon in the sense of a time-reversed black hole solution. The Big Bang is not such a horizon. The early universe was not a mouth releasing matter into pre-existing space, but the state of all space when the distances between regions were extraordinarily small. If there is a deep connection between them, it will not be captured by simply placing an equal sign between the two. It would require a new theory in which black holes, white holes, and the origin of the universe are understood within a broader geometry. Perhaps one day quantum gravity will show that the Big Bang was not an initial singularity, but a transition from an earlier state. Perhaps the universe once contracted and then rebounded. Perhaps black holes create new regions of spacetime in ways that outside observers could never directly witness. Or perhaps none of these models describes the real universe. What can be said with greater confidence today is that the standard Big Bang model does not require a white hole to explain most of the observational evidence. White holes remain a separate theoretical possibility, while the Big Bang remains our best description of the early evolution of the observable universe from a hot, dense state. Keeping this distinction prevents the story from becoming sensationalized. The universe does not need to be a gigantic white hole to be extraordinary. The expansion of space, the ancient light still traveling toward us from every direction, and the fact that every atom in the human body once belonged to a universe far hotter and denser than it is today already carry immense depth. Nor does a white hole need to be attached to the Big Bang in order to be fascinating. The possibility that it could be the late phase of a black hole or a time-reverse solution within the geometry of spacetime is already enough to illuminate a region of questions that physics has not yet closed. Between these two terminus lies a beautiful silence, or knows past, and in the distant future of black holes, if rebound models contain some part of the truth, there may be moments of very late release from regions once thought to have no way out. At one end, the young universe opens outward. At the other, an ancient black hole may return some form of energy. The two are not necessarily the same phenomenon, but both suggest that nature's most extreme states, may not be as silent as intuition imagines. They create boundaries and then force physics to learn how to move slowly across them. If the Big Bang was not a white hole in any simple sense, the question of white holes does not disappear. It simply returns to the place where it belongs, beside black holes, singularities, the information paradox, and quantum gravity. The Big Bang provides a wider context, showing that extreme states may be connected to the very origin of space and time. But transforming the white hole from a mathematical possibility into part of astronomy requires more than a resemblance in imagery. It requires signatures. It requires predictions. It requires a way to distinguish an ordinary cosmic outburst from a genuine causal structure that allows everything to leave and nothing to enter. So after passing through the Big Bang, the story does not end with an equal sign between two mysteries. Instead, it becomes clearer through a gentle dividing line. The Big Bang describes the expansion of the universe from an early hot and dense state. A white hole is a theoretical possibility involving a region of spacetime whose direction is opposite to that of a black hole, or perhaps the late phase of a quantum collapse. The two may illuminate one another through analogy, but each retains its own nature. And once that distinction is preserved, the next question becomes more practical. If a white hole is not the entire Big Bang, where might humanity search for its signs in the real sky? An idea can be beautiful within an equation, but to enter the real sky, it must leave a trace. The same is true of white holes. If a white hole is only the reversed shadow of a black hole in mathematics, it may remain a profound possibility that is difficult to test. But if one has ever appeared in the universe, however rare, brief, or faint, some part of it must have touched something humanity can measure. Visible light, gamma rays, X-rays, radio waves, high-energy particles, gravitational waves, or perhaps the unusual absence of a familiar source of energy. The modern sky is no longer observed through the unaided eye alone. A distant event may be recorded across many different wavelengths, as though the universe were telling the same story in several voices. Gamma rays carry the signatures of extremely energetic processes. X-rays often appear near hot gas, neutron stars, accreting black holes, or the remnants of dead stars. Radio waves can come from magnetic fields, plasma, pulsars, active galaxies, or very brief flashes that still hold many unanswered questions. Gravitational waves are not light, but ripples in spacetime itself, produced when compact objects, such as black holes or neutron stars, move with tremendous violence. If a white hole leaves a trace, that trace may not be contained within a single kind of signal. One place often considered is the realm of short-lived bursts of energy. The universe contains events lasting only a few thousandths of a second, a few seconds, or several minutes before fading away. They appear in the data like a lamp switching on in the distant darkness. Most of these flashes can be explained by processes that are already known or actively being studied. The collapse of massive stars, collisions between neutron stars, the immense magnetic fields of magnetars, matter being torn apart near a black hole, or activity within the centers of galaxies. A signal connected to a white hole, if such a signal exists, would need to differ clearly enough from these astronomical relatives. It would not merely need to be bright, it would need a distinctive pattern of brightness. That pattern might appear in the light curve, the way an event brightens and then fades over time. A stellar explosion often rises to a peak and gradually dims according to the expanding material and the decay of radioactive elements. A neutron star collision may produce a brief flash of gamma rays, followed by a fading kilonova as neutron-rich matter creates heavy elements. An accreting black hole may vary unpredictably, but its activity is usually connected to a flow of matter falling inward. A white hole, if it represents a delayed release from a region of space-time that was once sealed away, might produce a fading pattern that does not fully resemble any of these processes. But recognizing such a difference would require enough data, enough events, and observations made at precisely the right time. The signature might also lie within the spectrum of the light. When light is separated into its different wavelengths, It carries the fingerprints of the matter that produced it or that it passed through before reaching Earth. A supernova may reveal traces of hydrogen, helium, silicon, iron, or other elements, depending on the original star. A kilonova may be associated with heavy elements formed in matter ejected from neutron stars. Hot gas around a black hole can emit X-rays in characteristic patterns. If a white hole event lacks the ordinary layers of stellar material around it, or if the emerging matter has passed through a very different extreme state, its spectrum might not match familiar templates. Yet an unusual spectrum alone would still not be enough. Dust, distance, the galactic environment, and incomplete data can all make an ordinary event appear stranger than it truly is. Another possible path involves primordial black holes. These are hypothetical black holes that may have formed in the very early universe, not from the deaths of stars, but from unusually dense regions when the cosmos was still extremely hot and compact. If they exist, some could be far smaller than black holes formed from stellar collapse. Smaller black holes have higher Hawking temperatures and shorter evaporation times. In some models, small primordial black holes may also be connected to a transition into a white hole phase, or may leave behind extremely small remnants. If those remnants are stable, they are sometimes discussed as possible candidates for dark matter. But every link in this chain remains uncertain. Primordial black holes have not been confirmed as a clearly observed population. White holes have never been detected, and dark matter has many other possible candidates. Even so, this idea is compelling because it moves white holes away from enormous black holes that evolve far too slowly to be observed during the present age. A supermassive black hole at the center of a galaxy may require timescales vastly longer than the current age of the universe before Hawking radiation becomes important. But a very small black hole, if one has survived since the early universe, could evolve much more quickly. If any small black holes are now approaching their final stages, they might produce energetic flashes or leave unusual features within the background radiation. Gamma-ray telescopes, X-ray observatories, and wide-field sky surveys could search for rare, brief events that do not match any known source. A white hole signature might not be bright at all. If extremely small white hole remnants exist and remain stable for immense spans of time, they could be almost completely dark, interacting mainly through gravity. Searching for them would then resemble the search for dark matter, not by detecting the light they emit, but by observing their gravitational effects on brighter objects. Yet the influence of small, scattered dark objects is extremely difficult to separate from other possibilities. Gravitational microlensing can reveal dark objects passing in front of background stars by temporarily magnifying their light. The distribution of dark matter in galaxies, the motion of stars, and the large-scale structure of the universe can also place limits on such objects. For a white hole remnant to become a serious candidate, it must not only exist within a model, but also remain consistent with every observational constraint already in place. Fast radio bursts also often enter the imagination when brief and mysterious events are discussed. They are extraordinarily powerful, extremely short radio pulses arriving from beyond our galaxy. Many sources may be connected to highly magnetized neutron stars or extreme plasma environments. There is no firm reason to identify them as white holes, but they remind us that the universe still contains fleeting signals that humanity has only recently begun to classify. An unusual hypothesis should never replace a more natural explanation without evidence, yet transient phenomena remain one of the places astronomers search for new signatures, because rare events sometimes reveal themselves for only a moment. The modern archive of the sky is now so vast that many signals are not understood when they first appear. Automated systems detect changes in brightness, send alerts, and prompt other telescopes to turn toward the same location. Some events are classified quickly. Others require weeks, months, or years to understand. A white hole signal, if one exists, might begin its scientific life as a small entry in such an archive, a brief flash, an unusual spectrum, a fading pattern that does not fit, a location without an obvious host galaxy, or an energy source with no conventional explanation. It would not arrive carrying its own name. Humanity would have to interpret it through elimination, comparison, and patience, while waiting for further evidence. The search is not limited to light. Gravitational waves have opened another window onto compact objects. When two black holes merge, they produce a highly characteristic signal, a rising chirp that increases in frequency and amplitude before fading as the newly formed black hole settles into a stable state. If the interior structure or event horizon of a black hole differs from the classical description, some models suggest that very faint echoes might appear after the main signal, or that small deviations could emerge during its final stage. These ideas remain debated and are extraordinarily difficult to test because the signals are weak, the data contain noise, and classical black hole models have matched many observations remarkably well. Still, gravitational waves allow us to ask questions about horizons and the regions near black holes in ways that light alone cannot. Any possible white hole signature in gravitational waves would have to be treated with extraordinary caution. A single weak oscillation after a merger would never be enough to claim the discovery of new physics. It would require many events, multiple detectors, independent analyses, and a model explaining why the signal should appear at a particular frequency, time, and strength. Modern astronomy has learned that noisy data can produce remarkably convincing shapes when the observer is too eager to find what they hope to see. For that reason, silence in the data also has value. It helps place limits on models and narrows the regions where white holes or quantum rebounds might still remain hidden. Another area of investigation lies in the final stage of black hole evaporation. According to Hawking radiation, the smaller a black hole becomes, the hotter it grows, and as it loses mass, the process may accelerate. If a small black hole ends with a burst of energy, or if it enters a white hole phase instead of reaching a classical endpoint, it might produce flashes of gamma rays or high-energy particles. But no observation has yet confirmed such an event from an evaporating black hole. Current limits have ruled out some possibilities for the abundance of small primordial black holes, though many uncertainties remain depending on their mass, distribution, and emission models. This is one of the places where white holes, primordial black holes, and the physics of the early universe sometimes meet within the same search. There is a very slow rhythm to the way science moves through possibilities like these. A model makes a prediction. The data are searched for a sign. Finding nothing is still information. Finding an unusual signal begins an even longer process of testing. Many beautiful hypotheses have disappeared as observations improved. Many phenomena that once seemed mysterious became ordinary after humanity learned more about neutron stars, plasma, magnetic fields, cosmic dust, or distant galaxies. A white hole, if it is to survive within observational science, must travel the same path. Its mystery offers it no protection. It must stand in the light of the data. This makes the search for white holes both difficult and strangely peaceful. No loud pursuit is required. There are only observatories watching the sky night after night, detectors recording the smallest vibrations of spacetime, and archives being examined again whenever theories change. Signals once overlooked may be seen differently through new eyes. The universe does not hurry to reveal its rarest structures. An event lasting only a fraction of a second may require years of analysis. A flash from billions of years ago may become a new question only after several telescopes assemble its scattered pieces. Within this picture, possible signs of a white hole may lie in three broad places. The first is among high-energy transients, where a flash or burst of energy fails to match established models. The second is among extremely small remnants or dark objects, where a white hole produces little light but leaves a gravitational influence. The third lies in very subtle deviations within gravitational waves or in the final stages of a black hole, where the event horizon and the interior structure may not perfectly follow the classical description. All three paths are difficult, and all three must be approached with patience rather than certainty. At present, none of these paths has led to decisive evidence. Strange flashes may have other origins. Dark objects may belong to many different classes of dark matter candidates. Deviations in gravitational wave signals may come from noise, incomplete models, or more complicated astrophysical processes. White holes have not yet entered the catalog of confirmed objects. They remain possibilities beneath several layers of testing. Each new observation does more than search for them. It also clarifies where they can no longer easily remain hidden. The absence of evidence has value of its own. If gamma-ray surveys fail to detect the bursts predicted by a particular model, that model must be changed or restricted. If microlensing surveys do not reveal enough dark objects within a certain mass range, white hole remnants in that range cannot make up too much of the dark matter. If gravitational waves from many mergers continue to match classical black holes extremely well, large deviations near the event horizon become harder to accept. Science is not built only through discoveries. It is also built through quiet limits, as the possible regions of an idea gradually grow smaller. Along this journey, failing to find a white hole does not diminish the beauty of the question. Instead, it reveals the difference between imagination and science. Imagination can open a doorway with a single image. Science must ask where that doorway would cast its shadow, what kind of light it would release, what echo it would leave behind, and why familiar explanations would not be enough. A white hole may begin as the reversed image of a black hole in an equation, but to become part of the observable universe, it must possess a signature of its own. Among the countless voices of the sky, perhaps one day, an unusual signal will appear with enough clarity. It will not match a supernova, resemble a neutron star collision, carry the signs of an accreting black hole, or fit any known radio source. And at the same time, it may agree with a specific prediction made by a black hole rebound model. At that point, the white hole would no longer remain only an idea at the edge of physics. Until then, however, the question must remain open, serious enough to search for, yet uncertain enough that it cannot be stated as fact. Between observational instruments and theoretical models lies a very narrow passage through which new ideas must travel. The white hole now stands within that passage. It needs quantum gravity to provide a more plausible origin. It needs the information paradox to give it a deeper reason. It needs the immense timescales of black holes to give it a rhythm of development. And it needs observation if it is to become more than a beautiful shadow in mathematics. Every searchable signature, even if it ultimately fails to confirm a white hole, helps humanity understand more clearly what occurs at the limits of black holes. After passing through the places where evidence might be found, the picture becomes more balanced. White holes are not dismissed simply because they have not been seen, but neither are they raised to the level of fact because they are elegant and symmetrical. They remain between those two shores, in the region where theoretical physics and observational astronomy must meet with patience. That balance leads naturally into the next part of the journey, the reasons many physicists remain skeptical, and why that skepticism does not make the question less compelling, but allows it to stand more firmly within science. The more beautiful an idea appears, the more carefully it must be examined. A white hole seems almost perfect in the imagination, a symmetrical counterpart to a black hole, a doorway that opens only outward, a delayed escape route for matter and information once held beyond the event horizon. But the universe does not always choose the most elegant images that mathematics allows. Between a valid solution on paper and an object that can truly form in the sky lies an enormous distance, filled with questions of stability, initial conditions, energy, time, the surrounding environment, and observational evidence. A classical white hole encounters difficulties in the very nature of its existence. If it is the perfect time-reversed version of a black hole, It requires a highly specific structure of spacetime, in which matter can only emerge and nothing from outside can enter. But the real universe is not a perfectly clean room where every condition can be arranged with absolute precision. Even the regions that seem emptiest contain background radiation, rare particles, thin dust, distant light, gravitational fields, and small disturbances passing through. If a classical white hole were touched by even these tiny disruptions, it might not preserve its ideal form. The elegant symmetry of the equations becomes fragile when placed within a universe that is never entirely silent. That fragility sets white holes apart from black holes. Black holes have a more natural path to formation. A sufficiently massive star exhausts its fuel, its core collapses, its outer layers may be blown away, and the remaining core becomes a region from which light cannot escape. Black holes can also grow by consuming gas in stars or by merging with other black holes. Astronomy has observed many signs consistent with this picture: stars moving around invisible objects, X-rays from accretion disks, gravitational waves from mergers, and black hole shadows seen through radio observations. White holes have no comparable chain of evidence. No population of such objects has been identified. No classical formation mechanism as convincing as stellar collapse has been established, and no signal has forced the scientific community to give it that name. Another reason for skepticism lies in the arrow of time. In everyday life and in thermodynamics, entropy tends to increase. A broken egg does not put itself back together. Smoke does not gather itself into an unburned match, and heat does not spontaneously flow from a colder object into a warmer one without outside influence. A classical white hole resembles a film of a black hole played backward, and that reversal is precisely what makes it difficult to imagine as a natural process. A universe with a clear arrow of time does not easily produce states tuned with such extraordinary precision that the smallest disturbance could destroy them. The beauty of time symmetry in the equations does not erase the deep asymmetry of the thermodynamic world. Even when a white hole is understood as the final phase of a quantum black hole, the skepticism does not disappear. A rebound model requires a theory of quantum gravity powerful enough to replace the singularity with a finite region. It must describe how the event horizon changes, how information is preserved, how energy escapes, and how the entire process fits with Hawking radiation. Every part of that problem is difficult. It is not enough to say that matter is compressed and then rebounds. Inside a black hole, compression does not take place within an ordinary container. It unfolds within an unusual causal structure, where the meanings of inside and outside, before and after, are no longer as simple as they are in everyday examples. Different theoretical models also do not fully agree with one another. Loop quantum gravity may suggest a discrete form of geometry and a possible way to avoid a singularity. Other approaches follow different paths toward resolving the black hole information problem, perhaps by allowing information to escape through extremely subtle correlations in Hawking radiation, or by describing it through the holographic principle. Some pictures emphasize the role of a quantum event horizon. Others treat the black hole as a complex quantum system capable of evolving without any physical white hole ever appearing. When several theoretical paths remain open, an appealing idea alone is not enough to make one of them correct. The information paradox does not require white holes to exist. It demands that physics find a way to reconcile black holes with quantum mechanics. But there are many possible approaches. Information may be encoded within Hawking radiation in a way that was initially very difficult to recognize. It may be connected to the quantum structure of the horizon. It may be described through a holographic theory in which the information inside a region is represented on its boundary. Or it may pass through mechanisms that are still only partly understood. The white hole is a vivid possibility, but it is not the only possible way out of the paradox. Current observational evidence does not favor white holes either. The most powerful cosmic outbursts already have several well-developed competing explanations. Gamma-ray bursts may be associated with collapsing massive stars or colliding neutron stars. Fast radio bursts are more likely connected to highly magnetized neutron stars or extreme plasma environments. X-rays from regions near black holes usually come from hot gas in accretion disks. So far, gravitational waves from black hole mergers have agreed remarkably well with the predictions of general relativity. No signal has emerged clearly enough to require white holes to be added to the astronomical map. There may still be unusual signals hidden within the data, but that statement alone is not enough to turn doubt into confidence. The universe is always producing events that are not immediately understood. A strange source of light may be caused by dust, an incorrect distance estimate, a complicated galactic environment, a rare but already known object, or the limitations of an instrument. In science, a gap in understanding is not an empty space into which any hypothesis may be placed. It is a place where hypotheses must compete through specific predictions. For a white hole to stand on firmer ground, a model must say what signal it would create, at what energy, for how long, how often it would appear, and how it would differ from known phenomena. These requirements are strict, but they are not unreasonably harsh. They are how science protects its own curiosity. If every strange event were immediately given a new name, the sky would fill with beautiful but hollow conclusions. If every unproven possibility were dismissed too quickly, science would lose paths that might lead to discovery. White holes remain between those two extremes. They are interesting enough to continue thinking about, but they do not yet have enough evidence to enter the catalog of known objects in the universe. Skepticism also arises from the stability of the white hole phase itself. By definition, a white hole does not allow matter from the outside to enter. But if it appears in a universe filled with radiation and matter, its boundary must face incoming energy from every direction. Classical analyses often suggest that a white hole structure would be unstable. Quantum models may handle that instability differently, but they still need a specific description. A very brief phase might avoid some of the problems faced by a long-lived object, but it would also be harder to observe. A more stable phase would invite the question of why it is not disrupted by the surrounding environment. Whichever path is chosen, the model must pay the price in testable conditions. The lifetime of a black hole also pushes the question farther away. Large astronomical black holes may survive for immense spans of time. If the transition into a white hole occurs only after an extremely long delay, the present universe may simply be too young for most such events to have happened. This makes the idea difficult to rule out immediately, but also difficult to confirm. A phenomenon that may occur in the distant future can remain a reasonable possibility within a model, but astronomy still needs traces that can be searched for now. Small primordial black holes, remnants, background radiation, or rare transient events. Without such a bridge, the story can drift into a realm too distant to test. The same caution applies to language itself. Saying that a black hole may become a white hole sounds like a clear process, almost like water becoming vapor or a star becoming a white dwarf. But in black hole physics, the phrase "become" contains many layers. Does the event horizon still exist? Does the phase transition occur only inside? Or how does it become visible outside? What would a distant observer see? According to which clock is the transition time measured? How is information encoded? Does the escaping energy obey known limits? Until these layers are described more completely, the simple phrase must remain within the realm of hypothesis. Another reason many physicists remain cautious is that classical black holes have passed a remarkable number of tests. Gravitational wave signals from black hole mergers agree strikingly well with the predictions of general relativity. Images of black hole shadows at the centers of large galaxies are consistent with models of the region near the event horizon. The motion of stars around Sagittarius A times at the center of the Milky Way reveals an extraordinarily compact object containing millions of times the mass of the Sun within a very small region. These observations tell us nothing certain about the singularity inside, but they show that the exterior of a black hole is described extremely well by current theory. Any white hole model must preserve those successes before adding something new to the interior. This creates a constraint that is both elegant and difficult. A new theory cannot simply replace the part we do not understand. It must also return to what is already known and produce nearly the same results wherever the older theory has proved correct. If quantum gravity resolves the black hole singularity, it must still allow planets to follow the proper orbits, light to bend by the right amount, gravitational waves to travel in the forms we observe, and the exterior of a black hole to look like what telescopes have already revealed. The new doorway must open in the deepest region without bringing down the entire house whose upper floors have already been tested. On an emotional level, this skepticism does not make white holes any less compelling. It allows the idea to become more mature. A white hole accepted too easily would remain only a beautiful image, a white hole that must pass through doubt, observational limits, questions of stability, the arrow of time, and the information paradox truly belongs to science. Those obstacles reveal the real value of the question, not simply because white holes sound strange, but because they touch the places where humanity's deepest theories are still struggling to come together. In the end, nature may not create white holes at all. The singularity may be replaced by some other quantum structure that never releases matter in the manner of a white hole. Information may escape through Hawking radiation without any rebound phase. A black hole may evaporate through a more subtle mechanism, leaving no clear remnant behind. These possibilities do not fail merely because they are less beautiful. In physics, the correct answer is sometimes less intuitive than the image people most want to believe. It is also possible that white holes exist in a far more modest form than the imagination first suggests. Not as enormous doorways releasing entire universes, nor as strange white stars shining in the sky, but as an extremely brief phase of a small black hole, a quantum remnant, a faint signal within the background radiation, or an effect recognized only after enough data have been gathered. If so, white holes would not enter science through grandeur, but through small deviations tested over many years. The universe often reveals its deepest truths not through a tremendous explosion, but through a light curve that bends ever so slightly away from prediction. Skepticism, then, does not close the story. It simply keeps the door from opening too quickly. White holes remain at the boundary between mathematics, quantum gravity, and observational astronomy. They have no direct evidence behind them, but neither have they been completely ruled out in every model. They are questioned because they are difficult to form, difficult to stabilize, difficult to observe, and not the only possible solution to the information paradox. Yet those very difficulties would make any future evidence, if it appeared, far more meaningful. Behind all that caution, one question continues to rest quietly. Is a black hole truly the absolute end of collapse, or is the singularity merely the place where a classical theory loses its ability to continue the story? Is a white hole a real object somewhere in the sky, or only a mathematical shadow that helps us understand black holes more clearly? There is no need to answer too quickly. In science, some ideas must remain in uncertainty for a very long time before they are confirmed, revised, or allowed to leave the stage. White holes still occupy such a region, quietly forcing us to distinguish between what can be imagined, what the equations permit, and what the universe actually does. After passing through these layers of skepticism, the rest of the journey does not become darker. It becomes clearer. An uncertain idea can still change the way we see things if it points directly toward what our understanding is missing. White holes may not exist in their simplest form. A black hole may not rebound in the way early models imagined. Yet even the possibility makes the black hole seem less like an absolute full stop. If nature has found some way to avoid the singularity, preserve information, and carry the story across unimaginably distant ages, then the universe may be deeper than the pure darkness a black hole leaves in the eyes of an observer. If a black hole could truly pass through some deep phase and become a white hole, our familiar image of an ending would change dramatically. Black holes have long been viewed as places where the story of matter comes to a close. A star collapses, light is trapped, an event horizon forms, and everything that falls inside disappears from the view of the outside universe. But in a picture that includes a rebound, that darkness is no longer an absolute full stop. It becomes an immensely long period of transition, an interval in which matter, energy, and information are carried into an unobservable region, awaiting another form of evolution within the deeper structure of spacetime. The first change lies in how we understand the singularity. In the classical model, the singularity resembles a place where every path is forced toward an outcome that can no longer be described. Density becomes infinite, curvature becomes infinite, and space and time lose their familiar form. But if a black hole can transform into a white hole, the singularity is no longer a literal point where everything ends. It becomes a sign that the picture is incomplete, a region where general relativity must give way to a deeper theory. Instead of a final cliff, it resembles a layer of dense fog on a map, hiding terrain that present-day physics cannot yet see clearly. This change would not erase the black holes already observed by telescopes. From the outside, a black hole would still possess an event horizon, still bend light, still create a hot, luminous accretion disk when matter falls toward it, and still make space-time ripple when it merges with another black hole. None of what we already know would disappear. The new element would exist only in the deepest interior and the most distant reaches of time, where the classical description once left behind a singularity. A successful new theory would not replace the black hole with something entirely different. It would preserve the familiar picture wherever it has been tested, then continue the story beyond the point where the older equations fall silent. The second change concerns information. If matter falling into a black hole is not erased from the universe, but instead preserved, encoded, or eventually released in some form, then the black hole is no longer a place where nature loses its memory. A book falling into a black hole would not return as a book with all its pages intact. A star would not reappear with its former layers of gas, hot core, and familiar light. Yet the microscopic information describing its original state might not be destroyed completely. It could become deeply mixed into the quantum structure of the black hole, gradually dispersed through radiation, or, in some models, remain hidden until a white hole phase allows it to emerge in a form that is extraordinarily difficult to read. This picture makes a black hole feel less like a cosmic garbage disposal. It becomes more like a place of encoding, a region where the stories carried by matter are rewritten in a language that is almost impossible to decipher directly. Whatever falls inward no longer exists in its familiar form, but it may not be erased from reality altogether. In this view, the universe possesses a deeper continuity. Physical states may change beyond recognition, yet they are never completely severed from their past. That would be a profound shift, transforming the black hole from an image of absolute loss into one of extreme transformation. The third change lies in time. A black hole might become a white hole not according to the familiar rhythm of everyday life, but on a timescale stretched by gravity and by the immense lifetime of the universe. To an outside observer, a black hole could survive longer than generations of stars, longer than bright galaxies, and longer than the age when the sky still contains many sources of light. If a white hole phase ever appears, it may belong to a future so distant that the universe has become far colder, darker, and emptier than it is today. A moment in the deepest interior of the black hole could be stretched into a wait longer than any history humanity has ever known. In this picture, the universe contains more than events that are fast and bright. It also contains processes so slow that they appear almost motionless. A dying star may leave behind a black hole. That black hole may endure through eras longer than the lives of countless other stars. Deep inside, if the collapse reaches a quantum limit, the story may already have turned in another direction. Yet from the outside, all that remains visible is a quiet region of darkness. If a white hole eventually appears, it would not be the universe rushing to correct an error, but a very late echo of an event buried beneath gravity long ago. Such a universe would possess a greater depth of time than the familiar picture suggests. Black holes would belong not only to the deaths of stars, but perhaps also to the ultimate future of matter. When the final stars have gone dark, when star formation has slowed, and when galaxies have grown faint, black holes may remain among the most enduring objects in existence. Within them would rest the mass of ancient stars, gas and dust, past mergers, and astronomical histories that have receded into the distant past. If those black holes eventually evaporate, undergo a phase transition, or release energy through some deeper mechanism, then the far future of the universe may not be completely silent. It may still contain extraordinarily late events, rare and almost solitary within an immense darkness. This also changes the way we think about darkness itself. In everyday life, darkness is usually associated with absence, no light, no image, nothing to see. But black holes reveal that cosmic darkness can contain a great deal of structure. A black hole has mass, spin, an event horizon, and a gravitational influence on nearby stars. It can generate gravitational waves when it merges, carry immense entropy, and become connected to the deepest questions about information. If white holes are a real possibility, that darkness gains another layer, it may be the outward appearance of a process that has not yet ended. None of this means that every black hole is certainly the seed of a white hole. Caution must remain within every sentence. Rebound models have not been confirmed. White holes have not been observed. Quantum gravity has not yet taken on a complete, experimentally verified form in the extreme environment of a black hole. Yet the fact that this possibility can be considered seriously is enough to change the way black holes feel. The question no longer ends with how a black hole swallows matter. It opens into the deeper question of how nature handles its own limits. When a theory leads toward infinity, does the universe truly reach infinity, or does some deeper structure quietly prevent that from happening? If the answer points toward a deeper structure, black holes would become some of the most important places for understanding the nature of space-time. Space would no longer be merely the emptiness between objects. Time would no longer be only the steady rhythm behind every event. Both might possess microscopic structure, natural limits, and ways of responding to extreme compression. On large scales, space-time appears smooth like the surface of a calm lake. At its deepest level, it may contain fine grains, quantum cells, or a geometry that has not yet been fully named. A black hole is where that calm surface is pressed so intensely that its microscopic ripples can no longer be ignored. In a universe where black holes can become white holes, the contrast between going in and coming out also begins to soften. A black hole is the phase in which every path inside leads deeper inward. A white hole is the phase in which every path opens outward. If a quantum transition region lies between them, then these two directions no longer belong to entirely separate objects. They become two sides of a deeper process. Much as night and dawn are not two different worlds, but two states of the same sky as Earth turns. Darkness does not simply transform into light, but within the same evolving system, what was once hidden may gradually move towards some form of emergence. That image can easily become too poetic if it drifts away from science, so it must remain close to the limits of what is known. A white hole is not a promise that the universe always returns everything that has been lost. It does not turn the death of a star into a complete rebirth. It does not transform a black hole into a safe gateway for travel. It suggests only that the model of matter falling inward and then being erased at a singularity may not be the final picture. Matter may be transformed beyond recognition. Information may be encoded so deeply that it becomes almost impossible to read. Time may stretch so far that no civilization could witness the entire process. But absolute disappearance may not be nature's only option. The difference may seem small in language, but it is enormous in meaning. No longer visible is not the same as no longer present in the universe. Not returning in its original form is not the same as being completely destroyed. No evidence yet is not the same as not worth considering. These boundaries make science slower, but they also make it more honest. The possibility that a black hole could become a white hole remains a hypothesis, yet that hypothesis stands upon a real question. How can the event horizon, Hawking radiation, the preservation of information, and the avoidance of a singularity be brought together within a single picture? If that question is ever answered in a way that includes white holes, the universe may begin to look more like a system that hides things deeply than one that erases them. Whatever falls into a black hole would be removed from ordinary observation, but not necessarily from reality itself. Dead stars might leave behind not only regions of darkness, but also quantum states that endure for immense spans of time. The distant future could contain delayed echoes from stars that faded long ago. And instead of being only a grave for light, a black hole might become a place where nature's deeper laws preserve the continuity of information in forms humanity cannot yet read. Such a universe would also make humanity more humble. It would remind us that what can be seen is not the whole of what is happening. Telescopes can observe accretion disks, stars orbiting dark objects, gravitational waves from mergers, and black hole shadows against glowing matter. But the deepest interior remains beyond the reach of light. If that interior contains a quantum process, then reality has more layers than even the most beautiful image ever captured can reveal. Science may need not only larger eyes, but an entirely new language for describing regions from which light carries no information outward. This shift in perspective does not make black holes any less strange. It makes their strangeness deeper. A black hole is no longer merely a place where everything disappears. It becomes a place where general relativity, quantum mechanics, thermodynamics, and cosmology meet within a single question. It is a real object in the sky, but also a boundary of thought. It can be measured by its mass and spin, yet it may also contain a problem involving the nature of information. It appears within astronomical data, while its most important features lead toward ideas that remain untested. If white holes are connected to black holes, they only illuminate that boundary a little more. In the end, nature's answer may not resemble a white hole in the way we currently imagine one. A future theory of quantum gravity may replace the singularity with something that looks nothing like a white hole, nothing like a rebound, and nothing like any familiar image we are presently able to name. But even then, the journey through the idea of white holes would not have been useless. It has helped us ask the right questions. It has prevented us from treating the black hole as an ending too easily. It has forced us to take information seriously, to distinguish between time inside and time outside, and to recognize that the most beautiful explanations require both imagination and verification. In a universe that may contain white holes, endings do not disappear. Stars still die. Light can still become trapped. Black holes can still isolate matter from the outside world. But an ending does not necessarily mean absolute erasure. It may be a transformation that no outside observer can see at once. It may be a phase lasting longer than any familiar clock could measure. It may be the dark part of a process whose brighter phase, if one exists, lies far in the future. This does not make the universe easier to understand, but it gives it greater depth, like a piece of music whose lowest notes continue for a very long time before resolving into the next chord. At the end of this hypothesis, what remains is not a certain answer, but a different way of looking at darkness. Black holes may still be regions from which light cannot escape in the present age. They may continue to hide their deepest interiors from every telescope, but in models that attempt to move beyond the singularity, that darkness is no longer entirely silent. It carries the possibility of an unknown structure, a form of preservation we have not yet learned to read, and a future that classical physics cannot fully describe. And for that reason, even though no white hole has yet been found, The question of its existence makes the black hole feel less like a final period and more like a place where the universe is keeping its oldest and longest held secret. After all these layers of questions, the black hole still remains out there in the universe as a very real region of darkness. It does not need to become anything more mysterious to inspire wonder. The fact that light cannot return once it crosses the event horizon, that time near a black hole no longer passes as it does far away, and that the most elegant equations of general relativity lead to a place where they themselves begin to lose the ability to continue the story. These things alone are enough to make black holes one of the deepest frontiers of human understanding. White holes, if they exist, have not yet been confirmed as celestial objects. No telescope has pointed toward the sky and identified one with certainty. No signal has forced modern physics to place them on the observational map beside black holes, neutron stars, or supernovae. They still belong to the region between mathematics, quantum gravity, and the most distant possibilities of spacetime. Yet it is precisely this uncertain region that makes the question so memorable. Sometimes, ideas at the edge of knowledge do not provide immediate answers. Instead, they help us see more clearly where the true question lies. Whether a black hole can become a white hole remains unknown. In some models, collapse does not necessarily continue toward an infinite singularity. At extremely small scales, quantum gravity may alter the picture, preventing spacetime from being compressed without limit and opening the way to another phase in the distant future. In those models, a white hole is not a miracle, nor is it a brilliant gateway through which objects pass unchanged. It is only a possibility that the darkest part of a black hole may not be where the story is erased, but where it is hidden in a form too deep for humanity to read today. If that is true, the universe would not become simpler. It would become more complex, yet also gentler in the way we think about endings. A star could still die, matter could still cross the event horizon. Light could still become trapped so completely that no signal returned. But at a deeper level, disappearance from view would no longer mean disappearance from reality. Whatever fell inside might be broken apart, encoded, mixed together, stretched across time, and perhaps returned in a form that ordinary intuition could never recognize. Nature may also choose another path. White holes may not exist in the way current models imagine them. The information paradox may be resolved through more subtle features of Hawking radiation. The singularity may be replaced by a quantum structure that bears no resemblance to a white hole. The future of black holes may differ from every image our present language is able to name. Yet even if the white hole is not the final answer, the question still has value. It prevents us from understanding a black hole too simply as a hole that swallows everything. It forces physics to think about information, time, the limits of theory, and the deepest structure of spacetime. Somewhere out there, black holes continue to exist in the darkness between galaxies. Some were born from the deaths of massive stars. Others rest at the centers of galaxies, with masses millions or billions of times greater than the sunday. Some have merged with one another, leaving behind faint ripples that travel across the universe. They offer no hurried answers. They do not allow light to enter and then carry news back out. They simply preserve their boundaries, quietly bending space, slowing time, and revealing themselves through the motion of everything around them. Humanity observes those dark regions from very far away, standing on a small planet with a thin atmosphere, using telescopes, gravitational wave detectors, mathematics, and imagination to listen to what cannot be seen directly. There is something gentle in that image. A species that lives for such a brief time can ask questions about objects that may survive longer than stars. A mind formed from ordinary matter can contemplate places where matter is compressed to its limits. A small civilization can recognize that darkness is not always emptiness, but sometimes the place where the deepest laws of nature remain hidden. The final answer may still be very far away. It may require new observations, new generations of telescopes, more sensitive detectors, and a complete theory of quantum gravity. White holes may eventually disappear from physics as a beautiful idea that does not belong to the real universe. Or they may return in a more modest form as a brief phase, a tiny remnant, a faint signal, or an extremely delayed signature from black holes that have endured through ages beyond imagination. Whatever the outcome, the question has already done what a good scientific question often does. It has expanded the boundaries of curiosity without abandoning caution. And now, as this journey grows quiet, the black hole may be seen with a different feeling, not only as an abyss from which light cannot escape, and not only as the final state of a dead star, but as a region where the universe asks its most difficult questions about itself. Outside the event horizon, galaxies continue to turn, stars continue to shine, and light continues across immense distances. Inside, or within the region we cannot yet observe, there may be only the limit of an older theory, or there may be the seed of a new one. Thank you for joining the Sleepy Universe on this journey. As the night continues to settle into silence, distant black holes remain within the vastness of space, quietly holding light beyond their horizons. Perhaps they truly are the deepest endings nature can create. Or perhaps, in a future beyond every familiar clock, within regions where time has been stretched almost into stillness, some part of the story has not completely ended. And if the universe ever returns something from that darkness, its light will not merely be the light of a white hole. It will be a sign that even in the quietest place of all, another profound chapter may still be waiting to be understood.